We're now ready to start with the heavy lifting of high-performance computing, designing data structures for HPC. And since we're talking about concurrency specifically as the tool of HPC, we're going to look for log-free, partially log-free, and other efficient for concurrency data structures. And we're going to start with a shared pointer, which is one of the simplest things you can have, but very useful, often used a lot in the performance critical portion of the code, so needs to be maximally efficient. In general, when we talk about smart pointer in C++, it can refer to basically anything that looks like a pointer but isn't the built-in pointer. Typically, the reason a pointer is wrapped into a smart pointer class is because we want to do some additional actions on some of the operations with the pointer, often when it's constructed or deleted, sometimes when it's used. The common ones, and also the ones provided by C++11, are unique pointer, which automatically deletes the object when the pointer is deleted. Shared pointer, which is a reference counted shared pointer. It deletes the object when the last of these pointers goes away. And a weak pointer, which can point to a deleted object and knows when the object has been deleted. It's basically a safe dangling reference. In addition to these, there is a wide variety of smart pointers you can find in libraries or in your own applications. Some of them are for special functions for recording, tracking. Some are for debugging. You may want to know when memory is allocated. When you're referencing something, you may have a debug smart pointer that tracks dangling references or memory leaks and so on. We're going to focus on one kind of smart pointer, which is a shared pointer. It's a pointer that knows how many references to an object exist in the program. And I don't mean the C++ reference with the ampersand sign. I mean, in general, a reference as a way to get to this object. In this case, the way to get to this object is through this shared pointer. Of course, this works only as long as we don't use other pointers, such as built-in pointers or built-in C++ references to reference the same object. Otherwise, those cannot be tracked. And the correct application of such a shared pointer is to share ownership. When you have the object constructed, then it's used by multiple parts of the code, and each user is an owner in a sense that as long as at least one of the users is using the object should not be deleted. Shared pointers are sometimes used incorrectly in a context similar to this. You have a shared pointer and you call a function with that pointer. Within that function, you're not going to keep any long-term references. In other words, when the function is done, there are no more references to this object persisting past this point that were created in the function. So when the function is done, it doesn't retain the ownership. In this case, there is no reason to share the ownership. The function actually doesn't own this object. You can pass it a built-in pointer, a row pointer, because as long as the function is running, the caller is not going to do anything else. This is all one thread of context, and the shared pointer is going to stay on the stack of the caller until the function exits, so it can't possibly go away. But in cases where you have truly shared ownership, a shared pointer is a common solution to the problem. There are more than one way to do a shared pointer. Most of them are reference counted, although not all. There are other implementations. If you're dealing with a reference counted shared pointer, then your design has to answer several questions. Where to store the reference count? It has to be in some place where all copies of this shared pointer can access, so it can't be inside the shared pointer itself. What's the size of the shared pointer? It could be the same as the row pointer or different. How efficient is access of the data? If the shared pointer has a pointer to the data directly, then the efficiency is the same as the built-in pointer. There are implementations where you have to go through two pointers. Now, if you have the data that you want to access and the reference count that you want to maintain, there could be multiple memory locations. When you're doing different operations, you could be operating on one or more memory locations, which affects your cache use. Finally, in conjunction with share pointers, you may or may not need the weak pointers, which are the pointers that do not extend the lifetime of an object, but instead they know when they're dangling. Since C++11 has a shared pointer, shared PTR, Let's look at its implementation briefly, just so we have a starting point. It basically looks like this. The shared pointer itself, P, has two pointers. One points to data, to the object of type T. The other points to the reference count. There may be other stuff in that control block, and in fact, for weak pointers, there has to be, but basically it points to a block of memory where reference count and maybe other things are located. So what can we say about this design? It's larger than a built-in pointer, twice as large. It's as efficient for dereferencing. In general, the reference count and the data are stored in different memory locations. So if you have an operation that operates on both, such as deleting the shared pointer has to decrement the reference count and possibly delete the data, you will have two hits at different memory locations. For the purposes of this class, we're going to do another shared pointer design. But before we talk about other designs of shared pointer, let's consider the question of thread safety. We're going to do shared pointer in a multi-threaded context, so thread safety is of paramount importance. Is shared pointer as defined in C++11 thread safe? Well, it depends on what do you mean by thread safe. If you're talking about multiple shared pointers, maybe on different threads, pointing to the same shared object, then yes, it is thread safe, which implies that operations on reference count, incrementing and decrementing reference count, are done atomically. There is, however, another use case, which is if you have a single shared pointer that itself can be accessed by several threads. Maybe one thread will try to copy it, another thread will also try to copy it or dereference it. In this case, it is not thread safe. We will see why, but it's enough to know that the standard says it's not thread safe. You may want to have a shared pointer that is thread safe for the second context, which would be essentially an atomic shared pointer. Unfortunately, you can't wrap shared pointer in atomic, at least as the standard stands now. These two don't work together. There is work on creating an atomic shared pointer. It's a new type, but it's not in C++ standard as of yet, so it's not in C++ 14. At the time when I'm reading this, it's not in C++ 17 either. By the time you get this class, it may change. It'll probably make it eventually to C++, but for now we have to write our own. So it's important to know when to use, when not to use the shared pointer, and which guarantees they provide, when are they safe to use and when are they not. And that's not just for the C++11 shared PTR, but for any shared pointer you may write or get from a library. Okay, let's look at another design. But first of all, why bother? There may be several reasons. The shared PTR as it exists in C++ is a reasonable compromise between multiple competing requirements. You may have different priorities. For example, let's say you want to avoid two different memory locations as your first priority. Now, shared PTR has something called make shared, which allocates memory for both the data and the shared block, the reference count, in one contiguous memory location. If you always use make shared, then that problem is solved. Maybe you want to have your shared pointer to be of the same size as the raw pointer, which could be important if you have a lot of them. There may be other performance considerations. We'll see some benchmarks later. Also, there may be application-specific shared pointers, which are designed to integrate with your particular data structure, your particular application. They may do other application-specific things when they're operated on. Also, they may be less generic than C++11 shared pointers because you have some restrictions. You don't need something. For example, you don't need weak pointers. You could make a little bit lighter weight shared pointer. Here is an alternative design, one of alternative designs. There are many possible ways to build a shared pointer. This is the one we're actually going to use in this class, and we're going to use it later. So in a way, it's an application-specific shared pointer, and the application is being this class for us. It's called intrusive shared pointer, and the reason it's called intrusive is because the reference counter is part of the object that you're pointing to. It could be part of the data type itself, or it could be part of the larger data type that consists of the reference count and the data T that you want, but then you're always using that larger type R. Then you have only one pointer to R, and from that pointer you can figure out both the reference count and the data. So your shared pointer is the same size as the raw pointer. The dereference is the same as a raw pointer or shared PTR. One thing to notice, in this design, you cannot have weak pointers, because if the reference block R goes away, the reference count part of this block also goes away, so you can't actually have a weak pointer. Weak pointer needs something that stays behind when the object is deleted, so you know that the object is deleted and the weak pointer is dangling. So in this design, you cannot have weak pointers. You don't always need weak pointers. It has an advantage for us that it's also a little bit simpler, so we can focus on the matter of this class without being distracted by some of the complexities of other shared pointers. We're going to go through this shared pointer in a lot of details. We're going to build it in this lesson, but we're going to use it later. Now would be a good time to take a short break, and when we come back, we can formulate the requirements for the implementation and write some code. We're going to now look at the implementation of the intrusive shared pointer, but first let's formulate the requirements. What do we need from this implementation? It's a good vehicle for me to explain how shared pointers for high-performance concurrency are designed, but we're not actually going to do anything that is very specific to this particular design, so you can take these ideas and these methods and generalize them to other shared pointers. On the other hand, you may find yourself in a situation when the limitations of intrusive shared pointer or other simple shared pointer are acceptable, and then why not use it? Remember that generic shared pointers are, well, generic and they have some overhead associated with that. On the other hand, they are designed and implemented and tested by some very smart people, so you have to have some really good reasons to develop your own pointer. Having specific requirements is typically the reason. So now, is the intrusive shared pointer thread safe? Well, the simple answer is yes, because that's the goal. So it would have to be thread safe, because otherwise it doesn't serve our needs. So the better question perhaps is, okay, if it has to be thread safe, then how is it implemented? Part of it is manipulation of the reference count. Obviously, if you have two threads, both creating new copies of a shared pointer and they're pointing to the same object, both threads are going to increment the reference count. This has to be done atomically. It's a read, modify, write, so if you don't do it atomically, you can lose the increment. Now, in C++11, it's done by atomic fetch add, which in a single atomic non-interruptible transaction can increment or decrement the atomic variable. We're talking about thread-safe shared pointer. We're talking only about thread safety of the shared pointer itself. You can have two shared pointers that point to the same object of type T, and therefore two threads can attempt to operate on this object at the same time. This may or may not be thread safe. This is not our concern at this point. We're assuming that if you're designing your type T to be used in a multi-threaded data structure, it will be thread safe, or you will have locks on the client side. We're only concerned with the shared pointer itself not breaking. So it should point to the right object, the reference count should be correct. When the reference count drops to 0, it should delete the object, and so on. Let's look at the code for the intrusive reference counted shared pointer. If you compare this with the shared PTR of C++11, you will see that the shared PTR has a lot more stuff. This is not a class on STL design. I have simplified this shared pointer a lot. If you were to implement one like this in your own program, you would have to add at least some of the extra features that other shared pointers have. I have simplified it to focus only on the relevant parts of the code. Here is the way it's defined. So first of all, it works on two types. There is type T, which is what the pointer points to. There is also this type U, which defaults to T, and that's the wrapped type. It's the type that has both T and the reference counter in it. Now, if T has a reference counter already in it, then this is the same type for both. Otherwise, you need to create another class that will have T and reference count. There is a convention for naming. First of all, it operates on reference count using this addref and delref member functions, so type U must provide them. Second, type U must be convertible to type T. If U is derived from T, or if U is T, then this is done automatically. Otherwise, you have to write these operators. Okay, let's see how is it done. So first of all, we can construct the shared pointer from a raw pointer. That's basically how you get it for the first time. You call operator new to create an object of type u in this case, which would contain an object of type t, and you pass the result of operator new to the shared pointer. The shared pointer increments the reference count. Now you could create it with null, so we have to keep checking for null, but normally it increments the reference count. What happens when we delete the shared pointer? Well, if it's not null, we decrement the reference count, and the function delref returns true if the counter dropped to 0. So if the counter dropped to 0, we're going to delete the object. So far, we're going from reference count of 0 to 1 and back, but here is the copy constructor. This is what creates multiple copies. So we're going to point to the same object as the right-hand side. This is the right-hand side. I didn't show you. Let me scroll to the bottom. They all have inside just a raw pointer to the data and reference count, to the type u. Go back to the copy constructor. They point to the same location, and we increment the reference count by 1. Now, here is the other way to copy a shared pointer, and that's assignment operator. Assignment operator is more complex. So first of all, we have to check for assignment to self. If the left-hand side and the right-hand side are the same, we don't do anything. Then we're going to increment the reference count on the right-hand side, because there will be another copy of it. The left-hand side will point to the same pointer when we're done. We're going to decrement what this pointer, the left-hand side, points to, and we may have to delete the object. And we actually do need to check for null here. After we decremented our own reference count, we already incremented the right-hand side reference count here. Now we can just set the left-hand side to be the same as the right-hand side. Return reference to the object itself. That's a convention for all assignment operators. Well, to be useful as a pointer, you have to have operator star that returns reference to the object. The reference is the pointer inside. You have to have operator arrow that returns the pointer. This lets you use it in a pointer context. It's common for pointers to be convertible to bool, so they can be checked for true or false. It's false if it's null. Otherwise, it's true. We have this shared pointer, which is complex enough piece of code. It warrants its own testing. We're using Google Test for testing, so here is our test. Going to include the header, define some type. This will be our data. This is the wrapped type. We derive it from data. And then it has the reference count and all the functions to manipulate the reference count. The reference count needs to be atomic. We don't need copy constructor or assignment operator on this type. To make sure we don't do anything funny with the reference count, we remove these functions. Now, for the purposes of testing, it's nice to know how many of these B objects are currently alive in the program. So this is just for the test to run. We have this outside count, and we're going to count how many are created and deleted. Now, this is all single-threaded, so there is no problem with any race conditions. Now that we have this, we can run some tests. We can just construct the pointer initialized to null. We can construct the pointer initialized to a new object. Remember, it's a shared pointer to A, but it's initialized from an object of B. When you dereference it, it gives you back not B, but A. So when we dereference P arrow I, we're looking at I inside of the type A. And we're making sure that the objects are constructed and deleted as needed. We also have the tests for copying. That's kind of the bread and butter of the shared pointer. And we have the tests for assignments. If you're assigning and the left-hand side was the last reference pointer for this object, for what was on the left-hand side, has to be deleted. If you're assigning and the left-hand side was not the last pointer, so here we have 3 pointers. So the left-hand side wasn't the last one. There is one more. Like here, P and R point to the same thing. And then P gets reassigned, but R still points to that 42. In this case, it should not be deleted, and we have tests for all of these things. Runs, passes, everything is good. Of course, if you were actually building a more complete shared pointer for your application, you would have more tests as well as more features. So it works at least on one thread. Now that we know that this shared pointer operates correctly at least on one thread, the next step will be to check how it performs on multiple threads, whether it's thread safe. Before we do that, let's take a short break we come back and look at the behavior of this shared pointer in a multi-threaded context. We have just finished testing our shared pointer on one thread. Let's look at its thread safety. All reference counted shared pointers have this part of their design. This element is common. We have a shared pointer. Inside the shared pointer, you have a pointer to the reference count, and then somewhere else you have the reference count. It may be the only pointer you have in your shared pointer, like we have in our intrusive one, or you may have other pointers, but this group of elements is common to all reference counted shared pointers. And that's where the interesting things are going to be happening in the multi-threaded context. Dereferencing, pointing to the data, that's easy. So the tricky part is, of course, concurrently incrementing, decrementing reference count, and maybe deleting the object when n drops to 0. If one shared pointer is owned by one thread, then we don't have any problems, just like shared PTR of t doesn't have any problems, because our increment and decrement of reference count is atomic. So even if the two shared pointers point to the same object and they both change at the same time somehow, maybe deleted, maybe copied, we're thread safe. The problem case potentially is when two threads access the same shared pointer. We know that the C++11 shared pointer is not thread safe under these conditions. Let's think about our shared pointer. So let's consider what happens when you copy a shared pointer. It goes through several steps. First of all, you need to read the pointer to the reference count. And by that, I mean you would create a local variable where the pointer to the reference count is temporarily stored. So now you have two pointers to the reference count, one inside the shared pointer and one within the copy constructor, the function that is doing the copying. Once you have the pointer to the reference count, you can increment the reference count. That's the second step. So now we have extra reference to the object. And now we can finish building the shared pointer around this pointer to the reference count. Basically, the constructor of the new shared pointer completes at this point, and we now have two shared pointers, both point to the same object. The reference count has been incremented. There is no problem with constructing a new shared pointer when you have already incremented the reference count. So this is the potentially tricky part, reading and incrementing the reference count. If you have a race condition, this is where it would be. So let's see if you do. So let's look at the case when, while we're copying the shared pointer, another thread is trying to change it. So how could this be? Let's say that one thread is creating p prime out of p, and it may be assignment or copy. We don't care what happens to the old p prime at this point, so same thing for us. But another thread tries to do p equal q, so it's changing p to point to what q points to. And that happens at the same time. So this is our starting position. Q points to some other object m. Well, m is the reference count. There is also an object there somewhere. We don't care about that right now. Our pointer p has the reference count n and a pointer to reference count. We're going to begin the copy. And we begin the copy, we read pointer to n star. That's the first step because we need to increment the reference count. Have to get that pointer. Remember that the assignment is happening at the same time. And let's say assignment is proceeding right now. And what would the assignment do? It would move the pointer inside p from using n as a reference count to using m as the reference count. Now we have an extra reference to m, so it increment m to m plus 1. The assignment also decrements the reference count of the old p, the n, that was what p used to point to. Now it doesn't point there anymore, so there is one less reference. So n got changed to n minus 1. Now the assignment is truly done, and the copy that started on another thread, construction of p prime, is still ongoing, so let's finish that. We construct p prime from the pointer to n star is pointer to n, and when we construct this new shared pointer p prime, we have another reference to n, so we're going to increment n back from n minus 1 back to n. So now both the assignment and copy completed. This is the correct state. We have one more reference to m, and we have exactly as many references to n as we had before. Now, this is all good unless there was a special case. And the special case is n equal to 1 initially. Let's see why that is special case. We're going to go through the same steps, but n is now 1. We create a pointer to n. We're going to use it to increment the reference count. But before we get there, the assignment happens. The assignment redirects p to what q was pointing to, increments that reference count m plus 1, and decrements the old n to n minus 1. So from 1 we go to 0. 0 is special. Once the reference count drops to 0, the object and the reference count are going to be deleted. So now we have that pointer to a reference count that we are about to try to construct a shared pointer from. We're going to increment what it points to. We want to increment n, but the pointer is dangling. So this is not going to work. This is the reason why the shared pointer in C++11 is not thread safe, and unfortunately our intrusive pointer isn't doing any better. So what's so special about the assignment? Well, here is another way to look at it. Assignment operator essentially deletes its left-hand side. Let's look at this code, which is conceptually what assignment operator looks like. We don't want to assign to self, but that's common. Conceptually, this is what it does. It deletes itself, the left-hand side. In the case of a shared pointer, this destructor would decrement the reference count and potentially delete the object. Then it constructs a copy of the right-hand side in the memory that is still occupied by this object. We call destructor, but we didn't actually release the memory. This technique, calling destructor then without releasing the memory, placement new, constructing a new object, is called phoenixing an object. It's not illegal in itself. It kind of looks suspicious. It's actually legal. So this code may actually be a valid implementation of operator assignment. In the case of our shared pointer, it's not how we've done it, but it's close enough. The left-hand side did at least part of the destructor when we were assigning. So even though we didn't call destructor on the left-hand side in our assignment operator, we decrement the reference count and called delete. We did some of the work that destructor also does. You can kind of guess that if an object is being deleted and at the same time another thread is trying to access it, this is going to be tricky. If it's actually being deleted, it's going to be undefined behavior. Ours is not fully deleted, so we can try to get away with it, but so far we tried and didn't succeed. But that hints at the complications. You're trying to access an object that is being deleted while you're looking at it. We can take a totally different point of view, which is a concurrency-centric. We can say, okay, forget about the object. From a general concurrency-centric point of view, the problem is that we're doing two things. We're reading the pointer, n star, and we're incrementing what it points to, and we're doing it in two different operations. And somebody can come in between the two and mess things up, such as deallocate what the pointer points to. So the problem is that these two operations are not done atomically. When you put it this way, the problem should be easy to solve. We have to do it atomically, which leaves only the small matter of actual implementation. Nonetheless, do not underestimate the importance of this statement. It's part of factoring out pieces of the problem, breaking up the problem into smaller parts. If we have this read and increment atomic as a sub-operation, we can build on that. When you're designing data structures for concurrency, consider possible concurrent operations. Consider use context, what can and cannot happen on different threads, because there are multiple meanings to thread safety. You have to know what you're protecting against. How do we go about doing atomic operation out of taking a pointer, basically making a copy of the pointer, and incrementing what the pointer points to? I said atomic. I did not say necessarily log-free. So here is one. When we take the pointer, we can actually literally take it. We can do an atomic exchange of that pointer with null. Now, if we successfully did atomic exchange and what we got back is not null, we have the only copy of this pointer in the world. Nobody else can get to it because we just stole it with an atomic exchange. So now we can go and increment what it points to at our leisure, safe in knowledge that nobody can get to this reference count. Again, remember, this is thread safety protection against two threads operating on the same shared pointer. You can get to that reference count through another shared pointer that is owned by some other thread, but that's okay. Why is it okay? We have at least one reference to the shared pointer, the one we just grabbed through exchange. Therefore, the reference count has to be at least one, because one reference exists for sure. As long as it's one, nobody else is going to delete our object and our reference count. So we don't have to worry about them incrementing it and decrementing it. As long as that's done atomically using atomic increments, that's fine. It will go 1, maybe 2, 3, back to 2, back to 1. That's not dangerous. If we got back null from atomic exchange, which means somebody stole our pointer before we got there, well, we just have to wait. Loop on the atomic exchange. Eventually, we have to release the ownership, and we'll just return the old value into the pointer and star by an atomic store, at which point somebody else can get it. This is really a spin lock. It's a spin lock that is not using a separate flag, but is using the pointer itself as a lock. The interesting thing about these spin locks of this type, if implemented correctly, they can be really fast. We're going to get to benchmarks once we're done developing it all first and then testing. As promised, let's go straight to the code. Let's look at version 2 of this shared pointer. Now we are going to do the atomic exchanges or the spin locks, and we're going to encapsulate this spin lock into this structure, which is essentially a simplified spin lock class. So let's see what it does. You construct it with a reference to an atomic pointer. Why atomic? Well, our pointer to data that used to be just U star is now an atomic U star. So when you construct it with a reference to an atomic pointer, well, first thing it does is it keeps its own reference, and that's so it knows how to put the old value back. Then it also has a local pointer, and that's the place where we're going to stash the old value of atomic pointer when we steal it. Now, this is an optimization we have seen when we talked about spin locks. Before we go for atomic exchange, we're going to try to read it first, just read, and see if it's a valid pointer. You can see also we're not comparing with null. Why are we not comparing with null? Well, I didn't mention this before. On the slides, I said null, but that leaves us with one big hole in the design. If the shared pointer is actually null, which is a legitimate value for a shared pointer, it means it's not pointing anything. This lock would assume that it's locked, whereas in reality it's not locked, it's just null. So it would spin forever. So instead of doing null, we're going to have some value that a real pointer cannot have. For the purposes of this class, I'm going to use this. This is a hack. This is just the largest possible value for a pointer-sized integer, so it's FFFFF hex notation. If you run on Linux on x86, this actually is fine. You're not going to have that value in the pointer. How to make it portable? The standard says that this is somewhere between undefined and implementation specific. So how to make it portable? Well, you would have some static object and you would have a pointer to it, and that would just be an address that you cannot get from any other allocation because you already put an object there. Anyway, it doesn't matter. So this is a reserved value of the pointer, and this is what we're going to put into the pointer when it's locked. So first we read. If we read and it's not that locked, now we're going to go for exchange. We're going to try to atomically exchange what's currently in the pointer with the reserved value and capture back what was in the pointer. If it's still not locked, then we're good. We stole the pointer. So the pointer is now locked, and we have the old value here. We've seen if we didn't get it, then we have to spin, and we have seen this as a kind of way to break up CPU-intensive spinning when we talked about spin locks. Okay, so this is basically a spin lock. When the structure is deleted, it just stores the old value back. Let's look at the shared pointer and see what changed. The constructor did not change. The constructor from the raw pointer, at this point you have 0 references before you're done with it, so this actually creates the very first reference to the shared object, and you are still constructing this shared pointer, so no other thread will be operating on it because you haven't finished constructing it yet. This is a copy constructor. The first thing we're going to do, we're going to lock the right-hand side. We don't have to worry about the left-hand side, this pointer, the one we're creating, because we haven't created it yet. So we lock the right-hand side, then we're going to use this p inside the struct px. Reminder, that's this one here, that's just a raw pointer. Why a raw pointer? Well, we have the only copy of that pointer, we stole it. So there is no concurrency here anymore, this is a local variable. We're going to use it to add a reference. Now, other shared pointers that may be calling addref on the same object, but addref is atomic. So we're good. Now we're going to initialize our own atomic pointer. So we're constructing, remember? We're constructing, and we have to construct our data members. And our data member is this atomic U star. So we have to initialize it at some point. It's an atomic pointer, so you have to call store. We're going to initialize it with this value that we took out of the right-hand side. The destructor is implicit, called right here, and the destructor will unlock the right-hand side. So this is fine. The destructor of this object does very similar. We lock ourselves now, because again, since we're doing it thread safe, we now consider possibility that the destructor is running on one thread while somebody is trying to make a copy of the same object on another thread. So this is a bit unusual, but we'll actually make it work. So we're going to lock ourselves, and then we're going to decrement the reference count, if necessary, delete the object. Since this object that we're deleting is locked, if somebody else is trying to make a copy, either we get this lock first, in which case they have to wait, and they'll end up copying this null in the implicit destructor of getPTR. We will unlock. Now they can get to our object, but all they see is this null that we put into the pointer. So they'll get a copy of that. If the other thread that is running a copy gets there first, then we will block here. They can complete their copy. When they're done, we'll proceed to delete. That wasn't why we started this, although if you have a destructor running on one thread and copy running on another thread, you have to do this. But this is the assignment operator, which was the original source of all this trouble. So let's see how we dealt with the assignment operator. Assignment operator operates on two things at the same time. It has the right-hand side, and this pointer, this object, star this, is the left-hand side. They may be the same thing, so we deal with that. Okay, now we need to increment the reference count of the right-hand side. Before we do that, we lock it. So we lock the right-hand side, and then we increment the reference count on the right-hand side. Now we also need to lock the left-hand side, our own object, because maybe somebody else is doing a copy of this object at this very same time. Here is a potential pitfall. It's very easy to get both of these locks at the same time. Like if you didn't have these curly braces, you would first lock the right-hand side, and then you would lock the left-hand side. And why is that bad? Well, look at this code in the comment. Lock the right-hand side, lock the left-hand side, and on two different threads, we're running these two assignments. We're assigning A to B and B to A at the same time. So what's going to happen? Well, here, B is the right-hand side. So we're going to get a lock of B on one thread. A is the right-hand side on another thread. Again, this is now A on that thread. We're going to get a lock of A. And now both threads want to get the other lock, and they can't have it. And they'll wait for each other to release the locks they already have, which is not going to happen. See, there is no releasing of anything in between these two lines. So that's a deadlock. Deadlock is waiting for you every time you're getting two locks at once. You're trying to hold two locks at once. If two threads do it in two different orders, you're guaranteed a deadlock. To avoid that, fortunately, we have a simple solution. We're going to get the right-hand side lock, increment the reference count, and we're going to stash away the pointer in a variable whose lifetime is larger than this locked critical section. Why is this safe? Why can't this pointer dangle? Because the lock here will be unlocked here, but the pointer PXP persists. Why can't it dangle? Well, we added at least one to the reference count. And that one that we added cannot be taken away by any other shared pointer. Any other shared pointer keeps track of its own references. Add one, delete one. We have now sort of unbalanced one that will keep the right-hand side alive, no matter what else happens. So the right-hand side pointer cannot dangle. Okay, and then we lock the left-hand side. Once it's locked, we decrement the reference count, delete the object if necessary. And then we're going to store this pointer to the right-hand side into the left-hand side. Now, see this trick here. Remember that when this destructor of this getPTR fires, it's going to put the old value, the value that we saved. It's going to try to restore this P underscore. So whatever was in it before, it's going to put back, which is not what we want. We want this to go eventually into P underscore. So we're going to change the saved value inside getPTR. This, of course, plays fast and loose with the spin lock, but this is our embedded class. Nobody else is using it, so it's only used within this context. So it's okay. It's really just a way to essentially remove the common code that we use in multiple places into one place. So this is all really part of this shared pointer design. We're going to store PXP into the saved value of getPTR here. And then the destructor of getPTR, which doesn't know that we just swizzled the saved value, is going to store it back into the original atomic pointer, which is actually what we wanted to begin with. Notice that dereferencing doesn't take any locks. And that's correct, that's good and proper, because as long as we have this one shared pointer that we're dereferencing, there is again at least one in the reference count, so the object is not going away. Now, the single-threaded tests for it are exactly the same as for the previous design, and they pass. Don't underestimate the importance of tests. This is a simple transition from the non-thread safe to thread safe version of the shared pointer. I had one of these tests fail when I did it the first time. So we have our thread safe design, and it's at least as correct as the old one was, but is it really thread safe? Let's take a short break, and when we come back, we're going to analyze this pointer specifically, now with the view on thread safety. When we last left, we had an intrusive shared pointer that was thread safe, and we accomplished it by atomically taking ownership of the reference count pointer. So how fast is it? Well, that's the wrong question to ask. First of all, is it thread safe? It doesn't matter how fast it is if it's not thread safe. So is it thread safe? How do we test for that? We need somehow to test for thread safety of our shared pointer. Let's just run the tests on multiple threads. Let's see how we can do it. This is still a Google test framework, only we're now adding some threads to it. These are our types A and B, and here is our test. So this is what we're going to do. We have one shared pointer, and we're going to have two threads that are running this copyPTR function. And what does copyPTR do? Well, it copies the pointer, takes the shared pointer by reference, and creates m copies. We stash them in this vector, and it does it n times. So it's going to create m copies, delete them, create them again, delete them again, and this n times. And we have two threads doing this. That's just copying the shared pointer on two threads. Now, the really interesting problem, and the one we started from, that's why we're in this mess, is because of the possibility of assignments where one thread is assigning to the pointer and another thread is assigning from the pointer. So we're going to do the same thing. We have 3 shared pointers now, and we're going to do these cross assignments. Here's our cross-assign function. So it assigns to the first pointer from the second pointer. So it's P equal Q, Q equal R, and R equal P at the same time. Now, we don't know what the order will be, so sometimes it'll run 2 opposing assignments, like P equal Q and Q equal P effectively at the same time, and sometimes not, but we'll run it several times and see what happens. We ran it, and both of these passed. Why can that be? Maybe it's correct. Maybe we just haven't run it enough times. Maybe if we run it 1,000,000 times, we will find a data race. And maybe with this test, we can't find a data race, but it's still there. Just the timing doesn't work out right. Multithreading tests like this do not give you the guarantee of the correct behavior. They give you some assurances that it's probably more likely to be correct. Just to check, let's see if we apply exactly the same tests to our old first version of the intrusive shared pointer, the one we didn't have the spin lock. You can see that in this case, we found a race condition. We ended up losing an object. Again, this doesn't prove anything. This gives us some assurances that if we had races, maybe we would find them. It's better than nothing, and if that's all you can do, then do it. Better you find this in a test than you see that same thing happening in your program. But can we do something better? Maybe. We left in this unsatisfying place where we had some multi-threaded tests that may or may not find our threading bugs, although we had a partial satisfaction that we at least got lucky and our thread did find bugs in our first version that was not thread safe. But there are other ways. So I'm going to show you just one. So this is a TSAN, Google Thread Sanitizer. Here are the links to the TSAN itself and to its manual. The interesting thing about it, it's actually not a standalone tool anymore. It used to be, but now it isn't. It's built into recent enough GCC and Clang compilers. So if you have GCC 4.8 or Clang, I think 3.2 and older, you have it. Later compilers have better versions of this thread sanitizer. How do you use thread sanitizer? Well, let's see. So I told you that thread sanitizer itself is built into the compiler, so you need to write some code that you're going to compile. And this code is lifted wholesale from our multi-threaded test, so we're going to run the code that we already ran. Well, except it's not running in a Google test framework, so I had to change the Google test asserts to just plain asserts. But we run the test, so we don't expect these guys to fire. This is all the same code. It's running either copying or assignment on multiple threads. Also note that we don't have the Google test framework to run it for us, so we have our own main. And instead of test fixtures, we created these functions. We're calling them ourselves. Other than that, the body of the function is exactly what we had in the test fixtures. The secret sauce will be in the compiling. So first of all, I'm compiling with Clang. This is not an endorsement of Clang. Just on this machine, I have newer Clang than I have GCC, and I'm trying to run the latest version of the thread sanitizer. On your machine, maybe GCC would be better. In any case, you probably want to compile with optimization. You'll also want to compile with debug symbols, because if you do get any messages, they'll be better, clearer with debug symbols, but that's all kind of syntax sugar. Here is the essence. This is the GCC or Clang flag that turns on the TSAN. You need to link with the threading library, of course, to get anything with threads. Now, this line also ran it if it compiled, and we didn't get any messages. It means that it's correct. Well, just for curiosity, let's see what would happen if we did something that is known to make it incorrect. Let's see what would happen if we introduced a race condition into the program. So first of all, let's pay attention to these addref and delref functions here. Remember that they are supposed to increment and decrement reference count atomically, but that's not all they do. They also take bidirectional memory barriers, and that ensures that all the memory operations that were done before or after incrementing or decrementing the reference count are visible in that order. We also have another memory barrier, and that one is in the shared pointer itself. So in the original code for the spin lock, here we had an acquire barrier because we're acquiring a lock, and here we had a release barrier because we are releasing the lock. And I have just replaced them to remove all the memory barriers. So I have removed the memory barriers from the spin lock as well as from the reference count class. Let's force it to compile and run. Now the thread sanitizer gave us a lot of messages. You can analyze them and find out what they actually are, since I already know what they are because I just introduced that race condition. I'm just going to show you one more thing. In this particular case, the reason for the race condition is that we don't have the proper barriers on our atomic operations. Sometimes the reason is that you don't have the proper protection in the first place, but here we don't have proper barriers. TSAN has an option to run it with this environment variable. Run it, and basically it will change all atomic accesses to have a full barrier. It puts the barrier everywhere on all atomics, not just the ones we changed. See, now there are no messages. What this tells us is somewhere we messed up the memory barriers. So if all atomics had full memory barriers, we would have no problem. But the way things are now, without this, or if it's set to 0, we have races. So now we know it has something to do with memory barriers. Since we were the ones who broke it right now, we also know what exactly it is. Specifically, we know that this needs to be release. We know that this needs to be acquire. And we put the reference count barriers back. Now it runs clean. It may be tempting for you to basically remove all your memory barriers and then run TSAN and start adding them back until it runs clean. Don't do that. It's not guaranteed to always tell you the right thing. So it's a good tool. It's not 100% reliable tool, especially when it comes to memory barriers. Use it as another way to test your programs. It's not a guide for development by trial and error. We're done with TSAN. We're done with our thread safety analysis. Both our tests and the analyzer are now telling us that our new thread safe intrusive shared pointer is indeed thread safe. Remember that multi-threaded tests, which we have done, are good, but they're not actually a proof of anything. They do help you find bugs. If you find a bug in a multi-threaded test, at least you can fix it. So don't neglect that in your quest to be ideologically pure. If the multi-thread test finds a bug, it's a good way to fix the bug. If it doesn't mean that you don't have bugs. The analyzers, like the thread sanitizer, take a totally different approach to analysis. Between the two of them, we have reasonable assurances that we're doing good. So now we can finally legitimately ask the question, how fast is it? However, before we answer this question, let's take a short break. Welcome back. When we last left, we were wondering how fast our shared intrusive pointer is. We're now ready to talk about performance. As we start discussing performance, the thing that jumps immediately out at us is that we have a spin lock. It's not lock-free. Is it important or not? Remember, we were earlier benchmarking the simple increment, and we were comparing an increment using a wait-free operation. So we have an integer, we have a pointer to that integer, and we're benchmarking wait-free, which is just atomic increment on what the pointer points to. We're benchmarking spin lock, which is a pointer lock. In this case, it's spinning on that pointer. So in this plot, this is wait-free. This is the spin lock. And for this plot, I have also added lock-free implementation. Now we're benchmarking a compare and swap loop. So it's not wait-free, but it's lock-free. It's not using spin lock. It's just running compare and swap. The usual way it tries to increment. If the old value is still there, then it commits. Otherwise, it tries again. And this is the time in nanoseconds per increment on number of threads from 1 to 128. And I did really have 120 cores on this machine. You can see that on this machine, actually, spin lock is the fastest all the way up until the largest number of threads. And even then, it's beating compare and swap quite handily. The wait-free, which you would expect to be fastest, catching up at the largest number of threads. Don't just look at this chart and say, oh, lock-free programming is all bunk, we never need this. These results are strongly hardware dependent. This is exact same code, or literally the same binary, running on a different machine. This machine actually has only 80 cores, but more importantly, it's a different CPU, also Intel CPU, also x86, just a different model. So now wait-free is winning always. Lock-free is the slowest until the largest possible number of threads. And the spin lock runs in the middle, although it looks like it's going to cross over. So for a large number of threads, the spin lock is going to become slower. In general, these trends that you see here, the spin lock is doing okay, maybe better than wait-free, usually not, until you get enough threads, and then it starts to slow down. That's a general trend that you will observe. This is a benchmark for like a simplified case. We're just doing an increment on, let's say, the reference count, which is a little bit simpler than what we're doing on this shared pointer. We're not deleting anything, but it's kind of a worst case. It's a stress test. We're doing these increments over and over. We don't have additional operations that reduce the contention, because if you have some other code running between accesses to that reference count, that reduces the contention for the shared reference count. We can conclude that the spin lock, yeah, it's not lock-free. It's doing pretty well for the small number of threads. It will probably become slower than a lock-free for a lot of threads. Although, what's a lot of threads in our case? Remember, we're talking here about not all the threads that may be accessing the same object through different shared pointers. That's not where the spin lock is engaged, because our reference count itself, we just atomically incremented. That's wait-free as fast as it gets. But the spin lock gets engaged when multiple threads are operating on the same shared pointer, not the shared pointer to the same object, the same shared pointer. How many threads at a given time are going to be trying to copy or assign this one shared pointer. Well, in theory, all of them, but in practice, probably just a handful at a time. At least in many applications, that's true. So it may be plenty fast, and in fact, it may be the fastest for your application and for your design constraints. Maybe you have 100 threads total, 2 or 3 at most will try to copy the same shared pointer at the same time. Again, remember, we're talking about typical case. There may be once in a lifetime pathological case when all 100 threads hit the same shared pointer at once. It has to work correctly. It doesn't have to be very fast for this one unique moment in time. If it's not unique moment in time, then we have to do something else. But for many applications, this design will be fine. Performance isn't the only problem with logs. We had a whole class on performance and other problems with logs, and actually other problems were center stage. Performance was kind of barely mentioned at the end because it varies a lot. And the worst one is deadlocks. Fortunately, as long as you have these encapsulated logs where no user code, specifically no user code that can take another log, can be injected into the code that holding a log, we're safe. We're only incrementing and decrementing reference count under log, so we should be okay. Although we came dangerously close in the assignment operator where we could have taken both right-hand side and left-hand side logs at the same time. For very short critical sections, it's unlikely that you would have anything related to priority inversion or convoying or anything like that. But if you have special requirements, then you may be evaluating this problem with a different set of criteria in mind. For example, if you're a low latency or real-time system, your balance between log-free and logged could be different than just the pure throughput that we're interested in when we talk about high performance. So consider your requirements, but in a general high performance case, this is a fine implementation. I'm not going to actually show you the code for a true log-free shared pointer, and the reason is it would take me longer than this entire class. I'm going to sketch it and basically leave it to the student as an exercise. But this is how you would do it. If you wanted to have a true log-free shared pointer, your alternative to a spin log is, as usual, compare and swap. Compare and swap on some reference count. Not the main reference count, but now you need to reference count how many operations, such as copying, deletion, and assignment, are currently, at this moment, in flight on this one shared pointer. So it's going to be probably small per shared pointer reference count. So now your shared pointer will have the pointer to the reference block and a reference count. That reference count is not shared with other shared pointers pointing to the same object. It's only for this shared pointer. And we're going to count copies, assignments, deletions. We're not going to count dereferences, because remember, dereferences didn't need to be protected. We're going to run a compare and swap loop, and what we have to do is atomically read the pointer and the reference count and increment this reference count, showing that we have a copy operation in progress. Then the copy operation will increment or decrement the main reference count n as necessary, and then as the copy operation completes, we're going to atomically decrement the local reference count. We don't need to change the pointer to n, the n star. Compare and swap can fail, and it would fail because our pointer to the main reference count has changed, because somebody has changed the shared pointer that we're trying to copy. If that happens, we just go for another iteration of the loop. In the assignment, it's similar. Again, we have to atomically read the pointer and the local reference count, decrement the reference count because we just lost one reference to the object. We're assigning to point to something else. And then again, atomically decrement the reference count because our assignment operation is winding down. And at the same time, atomically write the new version of the pointer to the new reference block, so there cannot be an interruption between decrementing the local reference count and writing the new pointer. We have to handle the special case when we just deleted the last reference. This would be a true log-free implementation. It's not wait-free, it's log-free. What does it mean? If one thread is blocked, well, let's say operating system suspended it, there will be some other thread that will succeed on the compare and swap loop and will continue. It's not wait-free, and what does that mean? It means that one of the threads can fail the compare and swap for essentially arbitrarily long time. We have a thread that comes to compare and swap, and every time it does it, some other thread just happens to change the object before we did compare and swap. somebody is making progress, but not this one thread that is looping on compare and swap. Of course, eventually the other threads will leave that pointer alone, and then compare and swap will succeed. The important point is it's actually not necessarily faster than the spin lock. In our simple benchmarks for just the increment, we have seen that compare and swap is usually slower than a pointer spin lock. It may become comparable at a very large 128 number of threads. One thing for sure, this is a much harder implementation, which is actually going to negatively impact performance as well, because the reason it's harder, you have to write a lot of special code for handling various corner cases. This class is not about lock-free programming. This class is about writing high-performance code. If the high-performance code is not lock-free, use what's high performance, at least within the context of this class. If you did go for the lock-free implementation, here is one more hint for you. How would you actually do the atomic compare and swap on both the reference count and the pointer at the same time? Well, consider the x86 typical case. Pointer is 8 bytes, counter is 8 bytes. You have 16 bytes of data that you need to manipulate atomically. Well, on x86, you actually have what's called double cas, 16-byte compare and swap. Not available on other hardware. Even on x86, where it is available, it's really slow, and it requires special memory alignment, 16-byte alignment on x86. It'll actually crash if it's not aligned, at least on some CPUs. Another option, you may be able to, and this is non-portable and strictly speaking outside of the standard, but you may be able to steal a couple bits from the pointer. In HPC, this is a pretty common trick. What would you do to find those spare bits? Maybe your pointer points to, let's say, 8-byte aligned memory. So 3 lowest bits are always 0. On x86, you actually have a bigger target. x86 is 64-bit, but the address bus is not. It's 48-bit. The highest 16 bits are either always 0 if you are in a user program, or always 1 if you are in the kernel. In any case, they're always the same as the bit 47. You can store a 16-bit reference counter, the highest 16 bits of a 64-bit word, as long as when a time comes to use it as a pointer, you put it back together, you put zeros back in there. You can store it, you just have to restore it back when you use it as a pointer or when you use it as a reference count. The important thing to notice here is that the compare and swap doesn't actually care. It's not, compare and swap doesn't really operate on a pointer. It just operates on 64 bits. It just does a bit compare, doesn't care what the bits are. Fortunately for us, the reference count is actually probably going to be small. In 16 bits, it's short, so about 32,000 is the maximum reference count, and that's the number of threads that are currently trying to copy or assign this one shared pointer. Well, you may not have 32,000 threads on one machine. If you're worried about what happens if you occasionally overfill the very small reference count, well, first of all, you may actually not be in a position to do it if you don't have that many threads. If you do, then, well, you have choices. You can abort, you can leak some memory. There are options here. In reality, probably you will never do that, and you won't ever be theoretically in position to do it. Finally, one more option you can consider is you may use pointer that is less than 64 bits. And then you have legitimate space for your reference count. Pointer is a pointer. How can pointer be less than 64 bits? Let's say it's not a pointer. It's actually an offset into maybe some array or some other data structure, an array of these reference counts. Then, unless you have more than like 4 billion of them, the offset could be an int, 32-bit. Actually, doing this requires either a custom allocator, so your allocations are sitting in a compact chunk of memory, or it's also good if your objects of type T, and remember that the reference count now sits near the object, if your objects are stored in some sort of container, then index into this container, in fact, is small. It's limited to the size of the container, so unless your container is bigger than 4 billion, 32 bits is enough for you. But you would notice that all 3 of these are shortcuts. There is a fully generic implementation of a lock-free atomic shared pointer. It's really hard to do, probably not going to be faster until you have a lot of threads hammering on this shared pointer. If you're developing STL, you can't take any shortcuts, so you have to do that generic implementation. That's probably why it's not an STL yet. If you're writing it for your own application, do yourself a favor. Write something that is as simple as you can make it while satisfying all of your requirements. You have at least a chance of getting it right this way. What have we learned overall about shared pointers in general? when to use them, when not to use them. You may need a custom shared pointer. Now, it has to be justified. Fortunately for you, if you like implementing your own, if you're using shared pointers concurrently, you have a very good justification. C++11 shared PTR is not thread safe if multiple threads can access the shared pointer. Doesn't get any better than this as far as justifications go. If you decide to write your own, carefully consider what operations can be concurrent. Our atomic, not lock-free. It's atomic, meaning all operations are atomic transactions, but it's done with a lock. So our thread-safe shared pointer, for simplicity, it was intrusive shared pointer. You can do a non-intrusive the same way, was thread-safe against both the case when multiple threads using different shared pointers on the same object and multiple threads are using one shared pointer. When you go write your own, of course, do run tests. The first time you try it, you'll probably find some bugs. If you have access to an analyzer, use it to supplement the tests. And remember, always measure performance. Lock-free isn't always faster. It may be a lot harder. If you end up writing a lot of code because it's so hard, it may never get faster. It's not a purity test. It's working code that you're after. Measure its performance, have justification for doing it the hard way. Well, this was not a very hard way, right? So we're done with the shared pointer. For your own practice, if you want to get more experience, look at the other features that the C++ shared pointer has. It has some other operators and member functions, basically more interface. We didn't put it into the intrusive shared pointer because it wasn't necessary to explain the concurrency, but if you wanted to actually use that shared pointer in your application, you would need at least some of those missing features. So you may want to add them. Remember to add tests for all of them as well. Next time we get to use our new fancy shared pointer. See you then. Welcome to the next chapter of our class on high-performance programming in C++, and we'll continue our study of log-free and high concurrency data structures. In the previous chapters, we've looked in a lot of detail at a shared pointer, and now it's time to put the knowledge to use and look at some containers. We'll start with nodal containers. What's a nodal container? Well, in general, containers store your data. They divide into two types, at least the ones you commonly find in log-free or other efficient concurrent programs will be usually one of these two types. Sequential containers use a contiguous block of memory, like an array. Standard vector is sequential container. One of the things you have to deal with is what happens when that contiguous block runs out. Well, in a standard vector, it just gets reallocated. If you're writing a thread-safe container, you have some problems at this point as memory is getting swapped. This gets tricky. We'll consider those containers later in another chapter, but for now we're focusing on nodal containers. Nodal containers allocate every element separately in its own memory allocation, and they use pointers to hook them up in a single data structure. The advantage is you don't need to move the memory you already allocated, but typically you have more variables that you have to update in an atomic transaction. When you want to change this data structure, you would have some pointers, possibly several pointers per element, and they have to all be consistent with each other. Consider a tree, has 2 children per node. The other thing is the data structure itself may even be lock-free, but it allocates memory every time it adds a new node, and your memory allocation isn't usually lock-free. So these nodal containers are sensitive to the memory allocator when you consider their performance. So in general, you should be aware of hidden locks and hidden data sharing. malloc is a good example. It may take a lock. Not always does, but sometimes it does. And there is certainly a lot of shared data structures within malloc. For the purposes of this chapter, we will consider the simplest nodal container, which is a singly linked list. In the C++11 standard library has it, it's called forward list. That container in standard template library has fairly standard thread safety guarantees. As long as you use it on one thread, it's fine. You can read it from multiple threads as long as nobody's changing it. It has mostly familiar STL interface, begin, end, push front, pop front, things like that. But it also has some unique stuff which has to do with singly linked nature of the list. It doesn't have insert, it has insert after, it doesn't have erase, it has erase after. Because you can't actually delete an element that you're pointing to. It does have iterators, they point to elements, but you can't delete the element to which you're pointing, at least not in any reasonable time. You have to scan from the beginning of the list. To not put the head of the list in a unique position, it also has a before begin, which basically returns a pointer to the head and an iterator to the head in a sense. It doesn't have to be implemented this way, but basically iterator through before the first node. If you call erase after on the result of before begin, you'll be erasing the first node. Of course, popfront does that. Now, as I said, this is not thread safe, what you get in STL, so we want the same thing, but we want it to be thread safe. We'll end up doing more or less complete implementation, but let's start with just push front, pop front, and let's add one more because it's illustrative. We'll add find, which just finds a given element in the list. Now, find is not present in a standard forward list. You can just use find algorithm. The reason is it wouldn't give you any advantage to have it as a member. In a thread-safe list, it may give you some advantage depending on how the list is implemented. Knowledge of this thread-safe machinery may be helpful in writing a more efficient find. The algorithm find just runs the iterator along the list. Iterator is a generic accessor. Inside your own member function find, you may be able to get away with a simpler access than a full-blown iterator, could be more efficient. Now, before we begin the implementation, let's talk about the interfaces. Forward list has this particular API for accessing the front element. It has 3 member functions related to front. One is empty, returns a boolean. One accesses the front element, gives a reference to the front element, doesn't actually change it, just gives you a reference to it. You can only call it if the list is not empty, otherwise it's undefined behavior. And finally, pop front removes the front element. It doesn't tell you what it was, it just removes it. Again, you can only call it if the list is not empty. Let's imagine for a second that std forward list somehow was thread safe. So you could call any member function from any thread at the same time. It wouldn't actually do you any good because this is how you would actually remove the front element. If the list is not empty, you would take a copy of the front element by calling front and then pop front. You're going along this code, and here the list was not empty, so not empty is true. And somewhere while you're reading the front element, the list changes to empty. Now, we said that all member functions are thread safe, which means the call to front completes. That's what it means to have thread safe member functions. You can call another member function, such as erasing an element while this one is running, and the results are still okay. But now popfront has finished, popfront hasn't started yet. Now the list will be empty. We're going to call popfront on an empty list, the results are undefined. In order for us to have a thread-safe data structure, we first need to have an appropriate API that permits it to be used in a thread-safe manner. In general, it's a transactional API where actions you might want to take on the data structure are transactions. They're formulated in terms of like a single call. So another way to say it, to access the front element and pop the front element, you have to do it in one atomic transaction. Atomic doesn't mean here it's lock-free. It just means it's a single transaction. From your client point of view, it's non-interruptible. You can't do anything else on the thread on which you're doing it. Another thread can access the list at the same time, but from the point of view of the caller, this is just one call. You don't know what's happening inside. You can't get inside. The interface could be something like this. Pop front that returns the front element by reference if there is a front element to return, and returns true. If there was a front element, it's now deleted. If the list was empty, it just returns false, doesn't change anything, doesn't change the list, doesn't change the reference. It's not the only API, but it's as good as any other. They're all more or less the same, so we'll stick with this one. So remember, before you even start implementing a thread-safe data structure, make sure it has API that supports transactions. Let's start with the simple one, find. Find is a read-only function. It only accesses the list. As long as nobody else changes the list while find is running, we have no problem. Find just looks like this. We take a pointer to the first element, compare the value. If it's not the value we're looking for, next element, and so on. There is nothing interesting there. You can run multiple finds, of course. But now we're getting to something more interesting, push front. This adds new element at the head of the list. And it has to be thread safe, so this is what we're going to do. First, we're going to atomically read the head of the list. Why atomically? Because another thread may be changing the head at the same time. Then we're going to create a new node. So look at this pseudocode here. We read the head. Let's assume this is atomic. We create a new node with the value that we want to insert. And the next pointer, this second will be the next pointer. So this is the value, goes here. This is the next pointer, goes here. Will be the head, at least as we saw it first. Now the head could change. If it doesn't change, then all we need to do is point our head to the new node. But if it changed, we have to start all over again. This diagram would help. We create a new node, points to what head points to. We have our local value of head captured. We're doing the compare and swap, and head hasn't changed, so we're just relinking it to the beginning of the new node. This is our new list. Push front is thread safe. What do I mean by that? Let's say two threads are doing push front at the same time. The first one has created a node, hasn't linked it to the list yet. The second thread comes in and pushes another element, element 5, into the list. Note that the head has changed. It used to be like this when the first thread started. Now it's like this. It's changed. Compare and swap will fail. If compare and swap will fail, the first thread, the one handling T4, is going to capture the head again and point the element T4 to the new head, like this. Let's assume that this time nobody's changing the head, so compare and swap will succeed. Head will change. Now we have linked it to T4, then T5, and then the rest of the list. What about push front and find at the same time? Well, that's okay too. So let's say we have find going along, push front comes in, allocates the new element, hasn't linked it to the list yet. Our find continues, no problem. Push front changed the head of the list atomically. A new find will see either the old head or the new head. Well, we already have one that saw the old head, so let's get the one that sees the new head. This find runs along the new chain of elements 4, 1, 2, 3. No problem here. What does it mean that they're safe? It means it doesn't lead to undefined behavior if you call find and push front at the same time. It doesn't mean you're going to get something predictable. You will either see the new element or not. In this sense, it's predictable. You're not going to see something wildly different. But what exactly you're going to see just depends on the relative timing on calling find and push front. This is expected. This is normal. On this happy note, let's take a short break before we get to see things that aren't so thread safe. Welcome back to our exploration of nodal thread-safe data structures. The singly linked list, or the forward list, is the current subject, and we're moving from simple and thread-safe things to more dangerous things. The last function we have to implement is popFront. This atomically, transactionally removes the front element and returns it to the caller. Well, we already know how to atomically change the head and relink it to another element, so popFront is going to be similar. Atomically read the head, atomically read what the head should now point to. That would be the next pointer of the current head. We'll call it new head. Atomically replace old head with new head only if the head hasn't changed. If it changed, start all over again. If we succeeded, then the node we just unlinked from the list, the node that old head points to, cannot be reached by any other thread because no list pointers point to it. So we can copy the value out to the caller, delete the node. Now, of course, if head was null, just return false and do nothing. First, we relink the head to point to the next node. Let's assume compare and swap succeeded. The node that we just removed from the list exists only as something locally accessible from our thread. We have a local pointer that points to this node, but nobody else has it. So we delete it. What about push and pop at the same time? This is the first time where we actually run into problems. The problems are tricky. Doesn't manifest itself immediately, so let's walk through it. First thread is going to delete T1. So the first thing we do is we compute the new head that will point to next after T1, which is T2. While that's going on, the second thread comes in, actually successfully deletes T1. Why not? Doesn't stop there. That thread also deletes T2. Our first thread is kind of slow. We have the new head pointing to nowhere, but that's okay so far because the head actually has changed. Compare and swap will fail. Unless some other thread, could be the second thread, could be yet another thread, creates a new element, T4, but in the memory of the deleted element T1 at exactly the same address. Since we deleted T1, the memory was returned to malloc, could be reused again. And we just happened to be so lucky that we got that same memory back. Now, compare and swap is not going to fail, because the first thread saw the head pointing to this memory. It was pointing to T1, but the pointer doesn't know what it points to, only knows the address. The address is the same. Compare and swap is going to succeed, and this will be the final state. We will delete the first element in the list, which is now T4, because we think it's T1. We're going to point to what the old T1 element pointed to, which used to be T2, now it's gone, it's just a hole in memory. And this will be the final state of the list. Head points to deleted memory, and the entire list has been unlinked from the head. I don't know what's worse. It's not good either way. This is called ABA problem. It has a name. It's common enough in log-free programming that it merited this name. The reason it's called ABA is because the head in our case, but in general, some pointer, changes from A to B and then back to A. So the address cycles through A, then B, and then A, but the content that is stored in the memory is different. Compare and swap sees no changes because compare and swap compares addresses. Assumes that nothing was changed, and from then on, it goes badly. This can only happen as long as the memory of deleted nodes is reused for new nodes, because we have to get the same address again. Now, your memory isn't infinite, so eventually it has to be reused, but it's actually worse than that. The most efficient memory allocators typically will return the most recent memory first. Two reasons. One, it's probably still hot on the cache, so it minimizes cache misses. And two, some of the most efficient memory allocators employ free lists. The memory that just got released is inserted at the head of the free list, so that's what you're going to get if you want the same size memory again. The root of the problem is that while we're using these pointers in compare and swap as unique identifiers of elements in the list, they're actually not unique. They're only unique as long as the memory is not reused. For a slightly more obvious reason, calling find and pop front at the same time is also not safe. So let's say we have our find running, it runs along the list. Another find comes in, also runs along the list. Somebody calls pop front, delete the element that the find was pointing to before it had the chance to move off to the next element. Now, whatever's inside the find, we have some pointer. Could be an iterator, could be some simpler pointer, but we have a pointer to the node in the list. Well, that pointer just points to nowhere now. Find is not thread safe when elements can be erased at the same time. It goes beyond that, because find returns iterators to the list. Your callers will hold those iterators, and if list elements can be deleted, those iterators may end up pointing to deleted nodes. That's obviously not good. And the problem of push front, we already discussed the ABA problem. It's not limited to push front. Insert after is basically like push front, only instead of the head, it uses the next pointer of some element. So it has the same problem. You can see that all of these problems have one thing in common. They all happen when we delete nodes. If we didn't delete any nodes, life would have been great. We have to somehow only delete nodes when it's safe to do so. To do this, you need to know when is it safe to do so. So when is it safe to delete a node? When nobody has a reference to it. How could you have a reference to it? Insert after or push front, while it's doing its work, captures the address before the node where it's inserting. So push front captures the head, insert after captures the next pointer of the node after which it's inserting. Inside find, there is a pointer. That one also counts. Inside the list, of course, we have next and head pointers, they count. And we have any number of iterators returned by find or begin or insert after and returns an iterator. So any number of those, and then they can be incremented using ++, and they all have pointers. So all of those pointers are considered references to nodes. Can't delete a node as long as at least one of these things exists and points to the node. This would actually solve the ABA problem. Why would it solve the ABA problem? You can still get back the same address. But it solves the ABA problem because remember, the ABA problem was because the old head, the one we were doing comparison on, happens to be equal to the address of new node. Well, the old head counts as a reference to a node. It's the first one in this list, address captured by insert after or push front. So as long as you have that address captured, the node at this address cannot be deleted. If it cannot be deleted, you can't reuse its memory, so you can't get it back. So that's how ABA problem would be solved, if only we could do this. In general, deletion is probably the hardest problem in thread-safe data structures. Everything else is relatively simple, or much simpler anyway. In order to have safe deletion, we have to not delete anything that we might access by whatever means of access we have, including the internal. Fortunately, we have just the thing. The thing is shared reference counted pointer. That's exactly what it's for. As long as at least one of them exists pointing to the node, in this case shared pointer to a node, the node will not be deleted. And we just happen to have a thread-safe shared pointer that we built in the previous chapter. Now that was a bit of foresight. Let's take a short break, and then we come back and see how we use our thread-safe shared pointer to build a thread-safe forward list. Let's continue along with our lock-free list investigation. Last time, where we stopped, we had a lock-free list, kind of, and a list of problems with the lock-free list. I promised you that a shared pointer will magically make everything better. Let's see now how the same lock-free list behaves when we replace normal pointers with shared pointers. So this is our list, and this kind of box is a shared pointer. These are all normal pointers for now. Remember, we're only dealing with pop front, push front so far. So let's look at pop front. We're going to capture the new head as a shared pointer also. For the purposes of compare and swap, we need to keep the old head, but that will also be a shared pointer. And of course, the current list head is still there. So that's our attempt to remove element T1. Now we're going to reproduce the same scenario that got us into the ABA problem before. To remind you, the scenario was that at about this point, while one thread is trying to remove T1, another thread removes T1 and T2, but adds T4, and previously it was adding T4 in the memory formerly occupied by T1. So let's try to do the same trick. Here is our second thread. I don't show how it does it, but it removes T1. It removes it from the list, but we have a shared pointer now. Previously, this element was just gone. Now we have a shared pointer, old head, so the reference count is at least 1, maybe more if we have some other shared pointers, but at least 1. This node is alive. It's just not in the list anymore. From the head, you can't get to it, but there is this shared pointer pointing to T1. Okay, we remove T2. Now from the head, we go directly to T3, but again, T2 is still alive, and it's a little tricky, so let me show you again. This next pointer of T1 was pointing to T2, and next pointer of T2 was pointing to T3. That's still true, I just moved them around, but the linkage is the same. From T1 we can get to T2, from T2 we can get to T3, so these actually didn't change. The second thread is done with deletions, now it's going to create T4. It can't create T4 in the memory of T1 because that memory hasn't been released yet. So it'll have to create T4 somewhere else. Now we see why ABA problem doesn't happen anymore, because old head is not now equal to the current head and can't possibly be equal to the current head because T1 hasn't been deallocated, so you can't get T4 in the memory of T1. Compare and swap now fails. We're going to let go of the pointers to the old head and the new head, we're just going to throw them away. Basically, we're abandoning our entire attempt to delete the head element of the list. So old head and new head pointers go away, and they were the last pointers to elements T1 and T2. As soon as the shared pointers go away, the elements go away. The first thread is still continuing with its task of deleting the head element of the list, but it starts all over. It makes copy of the head, it makes the copy of the old head, it makes the new head, and it goes on the same way as it did before. But the important part is ABA problem is gone, we didn't corrupt the list. We correctly detected that delete, delete, insert sequence changed the list. Well, let's see how our other problem is doing. That's running find while we're erasing elements using pop front in this case. So find now uses a shared pointer. Creates a shared pointer, which is a copy of the head, advances it to the next element. Here comes the second find. Again creates a copy of the head. Here comes pop front. Nobody's interfering with it. Find is read-only. So pop front deletes the front element. But this pointer still points to T1. So T1 is not in the list anymore, but it's still alive, still points to T2. So our find is still okay. Now we moved the pointer. Let's say T1 wasn't the value we were looking for. We moved the pointer forward, and that was the last pointer to T1. Now T1 is gone, but that's okay because nobody refers to it anymore. You can get a new element in the memory of T1, of course, now, but that's fine because no compare and swap anywhere in the program will fail because you get a new element in the memory of T1, because nobody has an address of T1 as a shared pointer. If they did, T1 wouldn't go away. In general, we don't want just push front and pop front. We want insert after and erase after. And we just make an observation that insert after is basically like push front, only instead of front, it operates on the next pointer of whatever the iterator points to. Similarly, erase after is like pop front, but again, instead of the head, you start from whatever you point to, which for a single linked list really doesn't matter. You don't know what's before you anyway. So you can start from any of these next pointers. As far as you're concerned, this is the head of the rest of the list. All of our next pointers, all of our pointers in the list, head, next, and all of them must be shared thread-safe pointers. We have, as I said, a shared thread-safe pointer. Let's have a brief reminder of how it works. We have a whole chapter on them where we discuss different architectures, different designs of shared pointers, and the one we actually implemented and benchmarked was this one. Intrusive shared pointer, where the reference count was inside the block of memory pointed to by the pointer. So the data and the reference count were in the same block. It's as if we specifically designed this to serve as a node pointer in the list. How lucky was that? Because we control the node, so why not have a node structure that contains the data element and the reference count? It also has the next pointer in it, but we're not interested in that right now. This particular shared pointer, same size as a row pointer, quick to dereference, in general, a perfect fit for the forward list node pointers. Assuming, of course, it's thread safe. So is it? There are two non-trivial bits here. The first one is manipulating the reference count. Now that's easy, we just atomically increment and decrement it. And the second one is what happens when the reference count drops to 0. At this point, node gets deleted, and the whole point of this exercise with shared pointer, remember, was to safely delete the nodes, which is to say to not delete the nodes when it's not safe to do so. As long as one shared pointer is accessed by only one thread at a time, pretty much any implementation of the shared pointer will do, there is no problem. In our case, can multiple threads access the same shared pointer at the same time? Well, yes, the shared pointer lives inside the node, and you could have one thread calling insert after, and another thread could advance the iterator and then do something with this iterator, like erase the element. So you could actually have one thread erasing the element and another one is trying to access it at the same time. So you could have a pointer that is being changed and deleted at the same time. Changed and accessed at the same time, that's bad enough. You have an object whose destructor is running while you're trying to access it. That's going to be tricky. Let's see exactly what the problem is, and then we can see how to avoid it. Here is how we copy a shared pointer. We have a pointer to a node. Inside the node, we have a reference count. We have other stuff, doesn't matter right now. First, we have to read the pointer. Before you read the pointer, you can't change the reference count. Then we can increment the reference count. Now we make sure that the node stays alive. And then we finish building up our smart pointer from the raw pointer to the node. Now, why can't we make a copy of the smart pointer as another smart pointer? Well, smart pointer is a more complex object. The individual operation makes copy of bits. You can dress it up as a smart pointer, but the very first thing you did is you copied the bits of the pointer, the address. So this is where you run into the problem. Let's say we have two pointers, P and Q, and we're going to make a copy of P on one thread, and at the same time, change P to point to whatever Q points to. on another thread. And let's assume that P was the only pointer to its node. If it wasn't, then we're actually okay. Other pointers will hold both nodes alive, so nothing bad will happen. But P is the only pointer to its node. And remember that nodes gets deleted when the reference counts drops to 0. So this is what's going to happen. We make a copy of the raw pointer on one thread. That's our process of copying P into P1. We're constructing P1, so this is not assignment, this is a copy construction. While this is going on, another thread changes P to point to what Q points to. This has three effects. P points to what Q points to, the reference count of that node goes up by 1, the reference count of the old node goes down by 1, and down by 1 is 0. And 0 means the node gets deleted. And now our freshly copied pointer points to nothing, and we're going to finish building P1 from it. There is no way we can detect the situation. There is no way we can abort and do something else. So this is bad. There are multiple ways to avoid it. The simplest one is, and that's the one we have considered before, to basically run a spin lock inside the pointer. We atomically take ownership of the raw pointer inside the smart pointer using atomic exchange with null. And if your pointer can legitimately point to null, which usually you want to, then you wouldn't exchange with null, you would exchange with some reserved value which cannot be a real pointer. Doesn't matter for this discussion. If you didn't get back that reserved value, could be null, could be something else, then you're okay, but you did atomic exchange, so you now have the only copy of the true value of the pointer. You invalidated that shared copy inside the pointer. You can do whatever you want with the reference count. Nobody else can access it through that pointer. They can access it through some other pointer, but that's okay. Accessing reference counts through different pointers is done by atomic increments and decrements. There is no problem there. If you got back reserved value, such as null, then somebody else owns the pointer. That's, by the way, why you can't use null if you could have null pointers, because if you get back null, it could mean that somebody else uses the pointer. It could mean that it's a null pointer. So if you really have null pointers, you have to use some invalid address. For example, on x86, 64 ones is a good one. You can't get that as a valid address. Well, when you're done using it, you put the old value back, of course, again using atomic exchange. It's a spin lock, but it's pretty fast spin lock. Let's see exactly how fast. Let's have a short break, then we're off to see the code. Here is our atomic reference counted spin log base. So atomic in the sense of transactions, but not atomic in the sense of not lock-free. Shared pointer. We have encapsulated the machinery for this atomic exchange in this getPTR. And for performance reasons, you don't want to just hammer on atomic exchange until you get back your non-reserved value. You want to let go of the CPU periodically. Nanosleep is a good way on Linux. Schedule yield is another option. This is what we're using, and we use it every 8 times in this case. It's just an empiric value. Don't want to do it too often, don't want to hammer on the same pointer without letting go for too long. So measure performance, figure out what the best value is. Here is an interesting detail. We haven't seen it in the chapter on the shared pointers because there was really no need at the time, but you can see that it has a nested non-thread safe shared pointer. And how do we use that? We actually return it. Scroll down to where that is. When we want to dereference the thread safe shared pointer, it doesn't have a dereference operator. Instead, you can convert it to a non-thread safe shared pointer, and that you can dereference. That has operator star and operator arrow. And why is that? Well, if you could just dereference the intrusive reference counted thread safe shared pointer, you would get back a raw pointer. And then while you're holding that raw pointer, your object could get deleted because some other thread could delete the thread safe shared pointer. This way, you call get, you get back a shared pointer, and this guarantees that the reference count of your object is at least 1. Now, this shared pointer is not meant to be used by multiple threads. It's a local variable for your code that operates on the data. For example, it's what we will use inside the find. Multiple finds can run on multiple threads, but the code, the implementation of each find runs on one thread. So there, as long as you have this shared pointer, the node isn't going away. This shared pointer can be converted into a raw pointer, and you can use those raw pointers to access the node as long as you're holding on to the shared pointer and keeping the node alive. We're going to benchmark this shared pointer. So we have our fake node for the purposes of benchmark. The way the intrusive shared pointer is done, it needs the reference count to be inside the object. Here it is. And ours requires that the object has these two standard function names, standard for this implementation of the shared pointer. We have our own standard here. Add ref and del ref, that's how it adds and decrements the reference count. We can benchmark dereferencing. Remember, dereferencing the shared pointer is non-trivial. It gets you a non-thread safe shared pointer. We can benchmark a copy construction. We can benchmark just plain assignments or the cross assignment, two threads doing assignments in opposite direction. This is thread index 0, 1, 2, 3, 4. So half of our threads will be doing assignment in one direction and half in the other. The benchmarks are only as good as your comparison. So what are we going to compare it with? It turns out that your standard C++ shared pointer, shared PTR, has atomic operations on it. They're just not member functions. They're called externally. For example, this is the dereference. This is your std shared PTR, the regular one from the C++ standard template library. This atomic load explicit performs atomic load on it. You get back another shared pointer, and you can dereference it. It's the same shared pointer type, so the catch there with these functions is they are atomic and thread safe and so on, as long as this particular shared pointer is only accessed through these atomic. So there is atomic load, atomic store, there is compare and swap, and so on. Here is your copy. It's just a copy construction. For the construction, we don't need to be atomic. This object is being constructed. You can't get to it from anywhere else. Now, for the one we're copying from, we have to do explicit load. Well, here is atomic store. This is the assignment. We have to use atomic store and atomic load, and the same for cross assignment. Nothing prevents you, syntax-wise, from calling atomic load in one piece of code and just accessing this pointer, dereference it in another piece of code. And if you do that, your code is not thread safe. That's a problem with these atomic wrappers around std shared pointers. It's recognized as a problem, and there is a proposal for the standard committee to add atomic shared pointer. At the moment when I'm recording this, the proposal is for C++ 17. Again, at this point, it looks like it won't make it in C++ 17. It will be deferred to the later. By the time you read this, things may have changed. We can actually look at what's being proposed. The good thing about proposed additions to the standard, they come with code. We can get that code. It's pretty good code. These shared pointers have been vetted by standard committee pretty thoroughly. Maybe it can be made more efficient, but you would be hard-pressed to do so. So we'll benchmark that too. The current proposal lives in this namespace GSS. Now you see it has a member function load. That's that special atomic shared pointer, not in the standard right now, being proposed for the standard. It will have, just like std atomic, here is the atomic shared pointer. It's constructed from a plain shared pointer. Again, special shared pointer, the one paired up with that atomic one, not std shared pointer. Just like I do in my own shared pointer, there is matching shared pointer to go with a thread safe shared pointer. Has member function load. If we go to the assignment, that one has an overloaded assignment operator, which is atomic, also has a store. You can do it either way. Assignment operator actually just calls store, so it doesn't matter. We're going to benchmark all three of them. Let's run the benchmark for our intrusive reference counted thread safe shared pointer. We're measuring 4 different things: dereference, copy, assignment, and cross assignment. And we're doing it for 1, 2, and so on threads. Now, this machine only has 8 cores, so we're already running more threads than it has cores. And you can see that the real time is holding. It's going up a little, but overall, this pointer scales pretty well. CPU time is going up, so there is more and more overhead. Real time is creeping up, but we're way overcommitted. 128 threads on this hardware. Let's compare it with the standard shared pointer accessed through the atomic wrapper functions. Well, you can see right away it actually takes longer to begin with. dereferencing was 21 nanosecond, dereferencing the STD shared PTR atomically is 42 on one thread. Dereferencing it in normal fashion is a lot faster. It's the atomic dereference. The time goes up much faster than it did for our reference counted shared pointer, and CPU time also goes up. So there is more and more computing going on and takes longer. How does our atomic shared pointer do? Now remember, this is a proposal to the standard. It's written by some very good programmers. It has been optimized, it has been considered for efficiency, but there is a reason it's not in the standard yet. There's probably more that can be squeezed out of it. It's not the last word in atomic shared pointers, but it's a good reference point. You would be hard-pressed to find a better one. It seems to be running kind of similar to the STD shared PTR access through atomically. It looks like it's a little bit faster on this machine. I do have data collected on a larger machine, so let's go see that. Remember, we are benchmarking the locking shared pointer, that's our intrusive spin lock shared pointer, against shared pointer with atomic wrapper functions and the proposed atomic shared pointer. The two atomic shared pointers are fighting it out over here, but the spin-locked one is way faster. This is the copy. Same thing, although not quite as much difference. The shared pointer is a little better here. Spin-locked one is still better. This is our cross assignments. Again, the two atomic shared pointers are slower. Spin-lock is way faster. Now, why is that? Partly it's because the spin lock can be very fast. Also, it's not entirely a fair comparison. These atomic shared pointers are more generic than our intrusive reference counted shared pointer. For example, they both support weak pointer, which we're not using, but there is still some overhead related to the possibility of the weak pointer. There are some other things they do that our intrusive shared pointer doesn't. For one, they allow for the possibility of reference count being allocated in a separate block of memory. We don't, but just the fact that it's possible means that there is overhead. They have more data to shovel through. So it's not entirely fair comparison. A narrow purpose lock-free shared pointer would be better, faster than this more generic atomic shared pointer. Still, the spin lock is a viable contender. Maybe a very good lock-free shared pointer would be a little faster, but it has a lot to gain to get there. But what about the lock? Well, in this case, the lock is encapsulated in the pointer. So the list would be lock-free by itself. The shared pointer itself is not, but the list is, and if we can replace the shared pointer with a better one, if we got it, we could make the whole thing lock-free. Very important consideration is that this spin lock inside the shared pointer protects a very short critical section which does not contain any user code. You can't inject any other locks into it. So you can't deadlock. Basically, you can't hold another lock while holding the spin lock inside the pointer. So it's safe from deadlocks. In general, just because something is lock-free isn't necessarily faster. We have seen it in other chapters where we looked at the simplest thing, atomic increment. Spin lock-based increment is often faster than compare and swap-based increments. Now for increment, we also have the atomic increment. But encapsulated locks, which create atomic transactions, easy to write, safe to use, maybe very fast. Don't just chase lock-free for the principle of thing or the glory of it. Now we benchmarked the shared pointer. The only thing that's left is put it all together, look at the code for the entire list, test it, and measure its performance. Welcome back. Let's continue with our lock-free list. We tested and measured performance of individual shared pointers. Well, now we're going to have a whole lot of shared pointers. And here they all are. Our atomic forward list has thread-safe shared pointers for all the list pointers and same pointers in all the iterators. Now, the pointers inside iterators only need to be thread-safe if you allow the same iterator to be accessed by multiple threads at the same time. Otherwise, it's okay to have them be plain shared pointers. Remember that our thread-safe shared pointer has a matching non-thread-safe shared pointer that maintains the same reference count. So they work together. As long as at least one of the pointers of at least one of the two kinds exists, the node will not be deleted. Of course, we also have a lot of other pointers to nodes that are temporary local variables used for all the computing. That's what the temporary stored head address is inside the erase or insert for compare and swap. And all the other pointers, as long as we have in our code a shared pointer holding the node alive, we could also use regular built-in non-shared pointers, as long as something keeps the node alive. All right, let's see the code for the atomic forward list. Here is our list. Now, again, this is not an STL design class. If you look at the STL forward list, it has a lot more rigor to it. And if you wanted to build a complete library, you would need to follow at least some of the same guidelines. This just shows the bare minimum necessary to create a lock-free forward list. And it's intentional. I'm keeping it this way so there is no distractions, just the minimum necessary to create this list. So here is the portion of the node that links the nodes together. It has the reference count. Remember, we're using intrusive reference counted pointer, so it has to be inside the object. Has the next pointer, and that's basically it. It has the standard API for our shared pointer. Constructor and destructor just initializes the reference count to 0 and the next pointer to whatever you're linking it in front of. One thing that is not there, notably, is the data, and that's because it's the link portion of the node. It's not the node. The node is here. I'm using inheritance, and I'm not using virtual. I'm really tempting fate here because if I delete this object through the link pointer, it'll get spliced. The distractor of the data will not be called. I can get away with it because it's all internal to my list. You don't get pointers to node, at least not that you can use in the client code outside of the list. So as long as I am doing things correctly within the list code and never deleting derived objects by the base pointer, I'm okay. For example, you would notice here that this is a pointer to node. I don't actually have pointers to links anywhere. Well, the head is really kind of like a node in its own right, except it doesn't have the data. So let's go all the way to the end. And indeed, head is the link portion of the node. It's convenient to have a pointer to head stored here. That's what before begin returns. So it's just convenient to have it. Going back to the constructor now, the reason I went there to show it to you is because of this. Just to make sure that when I have a pointer to head and it gets deleted, nobody tries to actually delete head, I'm going to stick 1 into the reference count right here, and that 1 is not going away. So no shared pointer is going to try to delete the head node, and that's exactly the way I want it. It'll be deleted with the list object in the distractor. Well, the list has a clear function. I didn't mention it before, but it's kind of obvious what it does. It basically deletes everything in the list, the same as the destructor does, only you can clear it without calling the destructor. Empty. Our shared pointer is convertible to bool, and the read of the pointer is atomic there. Okay, here is push front. Capture the current head, create the new node. It's linked after the current head, but it's not on the list yet. And here comes our compare and exchange. It's compare and swap, but I'm using the same name of the member function as std atomic has. So my intrusive atomic shared pointer has this member function. Does exactly what compare and swap is supposed to do. It's a member function of the head. I'm giving it the expected value. I'm expecting the head to not change. If it changed, returns false. It takes this by reference, so assignment of the new head is actually embedded in this compare exchange. So I get the new head back if it changed. If it didn't change, then I'm done, basically. I linked the new node in. If it did change, I have to relink what the shared pointer points to. Again, the std shared PTR, and I follow this convention, can be relinked to point to something else by calling reset. It, of course, decrements the reference count of whatever it used to point to and increments the reference count of the new one. Eventually, this will succeed. Why do I return true? This is just convenience for Google benchmark. You'll see in a moment. A real push front is void. Now, pop front actually returns a Boolean. Can be true or false. It's false if the head is empty, or if the head became empty while we were spinning on compare and swap. What are we trying to swap here? Well, we got the head. We expect it to still be what we got, And if it is, we're going to replace it by head arrow next, essentially. Get just converts the thread safe shared pointer to the non-thread safe one, which is what we are using for these temporary variables. This is a temporary variable, doesn't have to be thread safe. No other thread can access it. We're going to return the date. Now, this H, the old head, it's a shared pointer, still there, which means the old head is still alive. So we can copy the data out. This may have been the last pointer holding it alive. So before we let go of this shared pointer H, we have to copy the data out. Then we return true. The list wasn't empty. We didn't cover the iterators in the slides, but I did tell you that insert after and erase after work with iterators, and they're basically the same as push front and pop front, only they use iterator instead of the head. Iterator is exactly what you would want it to be. This iterator uses the non-thread safe shared pointer because I decided that my iterators must be local to one thread. That's convention. If you really need iterators that two threads can access on, this is unusual. If you need it, you would have to use the thread safe shared pointer here. Most of the time, you get an iterator from a list that is shared between multiple threads, but the iterators themselves are only operated on one thread at a time. You could pass them to another thread, but you wouldn't have pointers to an iterators and give those pointers to two threads at the same time. As I said, if you need it, you can have a thread safe shared pointer here. The iterator has your usual operator plus plus. This is a forward iterator, single linked list, you can't go back, so no minus minus. Dereference. Dereference is safe as long as the iterator is alive, the shared pointer is alive, so this raw pointer we're returning here points to an object that isn't going anywhere. Remember that this is a link shared pointer, points to a node. We're actually returning a pointer to the data that is inside the node. Don't want to leak out any pointers to actual nodes. As long as we handle all of this correctly, the fact that we are playing loose with inherited classes is not going to bite us. Comparison operators, just compare where the position of the iterator is, the two comparison operators. Again, STL forward iterator needs to be derived from iterator traits, has all the type defs. I'm cutting this all out to focus only on the things I need for this class. In your own design, don't neglect those things. They're there for a reason. Now, here is how you get those iterators. Before begin, begin, and end. End is just an iterator with a null in it. Before begin actually is basically a pointer to the head, and begin is actually the pointer to what's after the head. That one could be null. Before begin can never be null. Insert after, as I said, very much like push front. Instead of getting the head, we get the next pointer of the current position of the iterator, create new node, swap it in as long as what the iterator points to did not change. By convention, insert after returns the iterator to the new node. Erase after, very much like pop front, get the current position, could be empty, in which case we'll return an end iterator. If it's not empty, we will return the iterator to what's after the erased element, which again could be a null iterator, could be an end iterator. Here is our member find. We're just using the shared pointers to nodes here. This is pretty similar to what we have inside iterator, so calling std find would probably not be unnecessarily burdensome in this case. Before it can be benchmarked, very important, needs to be tested. Now it's time to test our code. We have a whole lot of unit tests here, starting from simply constructing a list and all the push front and push front of several element, destructor, making sure destructor actually cleans everything, the pop front, before begin, begin, and incrementing and decrementing and comparing iterators, longer lists. You want to make sure that your list can actually hold more than one element. Insert after the head, well, that's push front, but it's also insert after on before begin. Should do the same thing. Let's test that it does. Insert after begin, that's not the same as push front, and we're testing that it isn't. Erase in different positions, find, make sure that it finds something that's there. Also, it doesn't find something that's not there. So our list has 1, 2, 3, finds 3, finds 2, finds 1, not finds 0. Have to test all of those things. we can run this, and all of it passed. The next thing would be the actual benchmark. Now we're going to benchmark several lists against doing the same thing, so I just factored out the actual test code. So this is what we're going to test. We're going to benchmark push front. Well, we're just pushing front. We're going to benchmark push front and pop front. So this push front and pop front leaves the list empty after each cycle. We're going to push a few elements and then push front and pop front. So now it's going to go from 3 elements to 2, back to 3, back to 2, not going to be empty. Maybe it makes a difference, maybe it doesn't. We'll see. Pop front on an empty list may be interesting if in your application list is often empty and a lot of your pop fronts fail. Maybe important how fast that is. Here is the find. So we're going to push some data onto it and then call find. This is the worst case scenario for find. It's going to never find it. Obviously, if it finds it, just find n sooner. So we're pushing everything from 0 to n find minus 1. We're looking for n find. In our case, we'll have 1,000 elements in the list. So it goes through the whole 1,000. I said I factored out common test code. So what am I benchmarking against? I'm benchmarking against cd forward list. And of course, a cd forward list is not thread safe, so I'm going to protect it with a mutex. For pop front, I have to protect with the mutex this entire sequence. Empty front pop. By the way, I promised to tell you why I made push front return bool. The only reason is so it can go into this do not optimize benchmark fixture, because this fixture requires the function to return something. In any real use, it would be a void push front. We already know that mutex is a pretty lousy lock, so we also have, for comparison, a spin lock based std forward list. Here is std forward list, same one, only now it's guarded by spin locks. So these will be our 3 competitors. Let's start with the mutex. 4 measurements: push front, pop front, and pop front 1. Pop front 1 is the one that never becomes empty. Doesn't look like it makes a whole lot of difference for this particular list. Really depends on whether something dramatic happens when a list becomes empty or not. For the std forward list, looks like nothing drastic happens. We're also running find on all the lists, but don't pay attention to the find on this list. I'll explain why later, but this number is actually meaningless. So ignore the find. Same for spin lock. Push front, pop front, empty pop front, they're all good numbers. Ignore what it returns for find, that's not useful. Unlike the mutex, which is here and it ran up to pretty high numbers, the spin lock list is actually holding pretty fast, even for a large number of threads. Well, finally, we're getting to the atomic. If these numbers seem kind of large, some of them are and some of them aren't when you properly look at them. We'll put it in perspective in just a moment. When I show you the measurements I collected, averaged over multiple runs and on a larger machine. Here is data of better quality and plotted in a chart. So lock-free, that's our atomic forward list. Mutex-based and spin lock-based standard forward list. This is push front. Mutex, we know it's kind of slow, but our lock-free list may be lock-free, but it isn't doing so hot. And spin lock is great. Push front, pop front combination, same thing. Empty list, pop front, lock-free. If you see what the code actually does, it's basically equivalent to a spin lock. It's very similar, so not surprisingly, it performs fast. There is no compare and swap in this case. It just looks at the pointer, detects that it's null, returns false. So far, it's hard to justify what we have done, but it's actually not that surprising. Spin lock uses one atomic variable to maintain synchronization. Our list has a lot of shared pointers. Shared pointers have their own reference counts that have to be updated. Those are shared variables. The pointer inside the shared pointer is a shared variable. So why did we do all of that? We did it because we actually support more than just push front and pop front. Initially, I've shown you pictures for just push front and pop front, but then I also added insert after and erase after. and find, and that's all supported by our atomic list. Our spin log-based list only supports push front and pop front correctly. It's not surprising that atomic forward list has some overhead, but why can't we use the spin log to support all those other things? There is a very good reason why, and we're going to see it right after the break. We have left it a somewhat disappointing state where our painstakingly designed log-free list didn't actually perform so well, but we did learn a valuable lesson from that. Don't over-design your data structures. If all you need is push front and pop front, you probably don't need the log-free list. Log-free list has more code than necessary for just push front and pop front, and more code typically takes more time to run it slower. Why do we need to go beyond logs for a full-featured forward list? Well, let's consider find. Find is not safe if we erase anything while find is running, which means we would have to lock the whole list while find runs, and that's order n, that's linear. Find, of course, takes a lot longer than push front and pop front, but if we locked the entire list while find runs, push front and pop front would take just as long if you happen to be doing it while find is locking. Well, that's bad, but that's actually not the worst. Find returns an iterator, same as begin or begin and then plus plus on an iterator. That iterator is safe only as long as the node that it points to is not modified. Now, obviously, it's safe only as long as the node is not erased, but it's worse than that. Without our thread-safe shared pointers, you can't access the node through an iterator if it's being altered, like made to point to another node. The node itself is not going away, but the next node is going away, and that's not thread safe. Basically, you either have to lock the entire list for as long as you have an iterator out. Well, that just makes the whole thing not useful. You got one iterator and the list is locked. Or you have to engage a log every time you're doing any kind of access on any iterator. You have a lot of iterators out there, and then somebody runs find, and all of these iterators come to a halt. You can't even dereference one of them because you're holding the lock on the entire list. Now, you could try to do a read-write lock. Find doesn't actually need to lock everybody. It only needs to keep writers away. So you can dereference an iterator while find is running, but you can't call erase after. But still, it's pretty bad because if find is running, or if you are advancing the iterators yourself, you can't call erase after on anything, anywhere. Again, you could say, well, I don't need to lock the entire list because I only need to lock the node that I'm pointing to, maybe the next node. So you could try to lock every node separately with its own spin lock. The problem now, you have a lot of spin locks, and if you try to lock two of them on two different threads in opposite order, that's a guaranteed deadlock. How could that happen? Well, for example, erase after needs to lock two nodes, the one it's pointing to and the one after that that's being erased. You could have two iterators on another thread to both of those nodes. You could access those iterators in any order, including the order opposite to what erase after does. Well, that's probably a deadlock if the timing works out right. This kind of accesses to a data structure where you're basically accessing every element everywhere at any time, all at once, many of them together, and all from different threads, you really can't do with locks at all. That's why I told you don't pay any attention to the times of find. Spin-locked list has a decent find on a short list. The problem is, if you are going to honor that time and take it at face value, you have to then say that push front and pop front could take that same time, and that's no good. So on a log-free list, what's the performance of the find? Here is the data, and here is something we haven't seen before. The time actually becomes shorter with the number of threads. I haven't explained it to you before, but this actually has to do with the way Google Benchmarks counts time. It's not a bad way to count it, you just have to know what it does. On a perfectly scalable program, if on one thread something takes, let's say, 1 second, on two threads, the two threads would either do half of this work in half a second each, or twice as much work in still 1 second, if it was perfectly scalable. So that's how Google Benchmark counts it. It takes a fixed amount of work, and it counts how much time it takes to do it on all of the threads. So if you had perfectly scalable program that divides work evenly between all threads and sharing no contention, no slowdown, you would have some time t, let's say 1 second on one thread, half a second on two threads, a quarter of a second on four threads, and so on. Find starts off actually pretty close to ideal. The dashed line here is this time, whatever it takes, and this is obviously linear in the size of the list, but then divided by the number of threads. Well, for two threads, it's perfect. For four threads, it's close to perfect, and it kind of deviates from perfect, but it actually still goes faster and faster with more threads. It plateaus around 100 threads. This machine has 60 cores with hyperthreading, so 120 hardware threads. So find actually scales really well. It's not perfect, but it's pretty close. Makes you wonder now about all these graphs we have seen before, which were flat at best or going up. They were never decaying. Well, that's because we've never seen anything like this before. We've never seen something that has a potential to scale perfectly. We've seen things like increment or push front, where we're accessing the same variable essentially from multiple threads. At best, it's going to cost you nothing to have the synchronization. So whatever it costs you to access on one thread will do it, then the other thread will do it. They can't both increment at the same time. Deep down at hardware level, one increment happens, then another increment happens. So at best, you'll have the same time for all threads lined one after the other when you're doing this. Anything else is overhead. This is the first time when we can actually see code that could scale well, and it does. So our lock-free list has a pretty good find. Remember, find is just an iteration over the list. So if you have your own iterators running around the list, this is the kind of performance you can expect. While we don't want to be over-designing the data structures, if you do need a data structure that has essentially distributed access anywhere, not just push front, pop front, or something similar, accessing just fixed points, but basically random access, multiple threads, multiple locations, moving up and down, only down in case of forward list at the same time, you may pretty much have to be lock-free or mostly lock-free. There could be some exceptional cases that you're handling with a lock, and there could be, like what we did with the shared pointer encapsulated spin lock that provides transaction on a very small scale. But there are cases where you really can't do with locks what you can do with lock-free, at least with any reasonable performance. And this list is one of them. Okay, before I let you go, have to burden you with some homework, don't I? I told you that if you have per node locks, you run the risk of deadlock. Can you actually write code that does it? Well, the first challenge, obviously, is figuring out under which conditions you could deadlock. The second challenge is get the timing right, which actually requires you to be pretty efficient in your code. That's the interesting part of the challenge. If that was easy enough for you, consider implementing a doubly linked lock-free list using any kind of thread-safe shared pointer. You can use just std shared pointer with atomic wrapper functions if you want. Doesn't make that much difference. Now that one with a lock, if you try to do a doubly linked list with a per node lock, that one is really easy to get to deadlock. You just have to traverse the list in opposite directions on two different threads, and that's it. Welcome to the next chapter of our class on high-performance computing in C++, where we continue our exploration of concurrent thread-safe containers. And in this chapter, we're going to talk about block containers. We have previously considered this division into two large classes. Nodal containers, such as lists, were considered in their own chapter. Their distinguishing feature is that they allocate every element in a separate memory. Then they connect the whole structure together with pointers. Sequential containers, on the other hand, allocate a contiguous block of memory, sometimes several large contiguous blocks of memory. But within a contiguous block of memory, we have an advantage of a natural order. So at least one way of getting from one element to the next element is to simply follow along the memory block. That's their advantage. Turns out that they are effective when your order of accessing elements is typically the order in which you follow them along the memory block. It is very cache-friendly, prefetch friendly, and it allows totally different kinds of lock-free and light lock synchronization than nodal containers, so they deserve their own separate study. Let's begin with exploring these containers. One thing to point out is that, particularly for nodal containers, but also for block containers, if you don't keep the same block at least, is that memory allocation may in fact contain locks and additional shared data elements that you do not explicitly see, but they will impact the performance of the memory allocation and through it your entire program. So that's something to keep in mind. Block containers are less vulnerable to it because typically they do not reallocate their memory. At least conceptually and often in practice, a block container is just a large contiguous memory region on which we impose some structure. So one end of it we call top, and that's where the data is added. Data can be removed from the same end, top, that would be the stack, or data could be removed from the other side of the block called bottom, that would be the queue. There are also containers where data is added, let's say, to the top, but it's never actually removed. Instead, the readers can read any data that's in the used portion of the container. Of course, eventually we'll run out of memory, so the old data elements just get overwritten then. It's a kind of a half queue. In this chapter, we will consider an example of the queue in details. Stacks and other block data structures are quite similar. When the data is removed in case of the queue, it leaves behind empty memory, which can then be reused for adding new data. Let's look at how this container is accessed by multiple threads. Before we do that, we should note that there are two kinds of threads here. There are producer threads or writer threads that add data to the container. There are consumers or readers that read data to the container. It's not entirely strict naming, unless you're dealing with the case where writers actually just write and consumers can read anything but not delete it. In a queue, your consumers have to actually delete elements from the bottom of the queue, which means they have to mark what was deleted. They have to advance the pointer or the bottom index. Very often in applications, producers and consumers are different threads, but sometimes they aren't. You could have the same thread both produce and consume at different times. Most of the time, having gone to the trouble of actually writing a block container in the first place, you would optimize it for your very particular need. For example, if you have only one producer thread, your container is much simpler than if you have more than one. So if you do have one producer thread, you take advantage of it. Not only it's much simpler, it's also faster. If you know that the capacity of the container can be limited and you know what it is in advance, you can simplify the out of capacity case because it would just never happen, and so on. Let's look at the queue from the point of view of the producer. Producers have a very simple task, at least their main task. So they have a boundary between used memory and free memory, indicated by the top pointer or the top index. Usually you use indexes for accessing into this contiguous memory block. You basically treat it as an array of elements and use indexes, but you can also use pointers. Here is what the producer does. It atomically increments the top index. Now the slot that was pointed to by the old top is reserved to that producer thread that did the increment. No other producer can see it because any other producer thread would see the new top. So a producer that successfully incremented the top pointer can now write data into its own slot. It doesn't have any race conditions with any other producers for this slot. So this slot belongs to the producer and producer writes data into it. This is very simple, wait-free addition of data. Now, if you have two producers, they both do their atomic increments. The two happen in some arbitrary order. Let's say first thread does it first and then second thread. They each now have their own reserved slots in the queue and they can copy their data. Of course, the producer that got the second slot could actually finish copying the data before the first producer. From the point of view of the producers, it makes no difference. It will make a lot of difference later, though. What does it mean to write data? Usually it means calling the copy constructor. You're copying the data element from the client's piece of data, from the object given to you by the client, into the queue. Although in C++11, there is also in place where you call the constructor in place. So either producer may finish first, eventually they'll both finish, and then you just have more used memory, which is initialized with client's data elements. When elements become ready in order, your conceptual picture of the queue holds very well. The used memory just grows. When elements become ready out of order, you have a gap in the used memory section, at least for a little while. Producers, as I said, don't care. But for consumers, it presents an interesting problem because now the consumers which scan used memory will eventually reach the unfinished element 1. They have to somehow know that it's unfinished, and we haven't provided any mechanism for that yet. Of course, we will. So let's assume that we have that mechanism working somehow. So now consumers will have to wait on element 1 to be finished copying. And if they somehow jump over and can access element 2, they will dequeue elements in the wrong order. And sometimes it's fine to dequeue elements slightly out of order. The application just isn't sensitive enough. If that is your case, take advantage of it. It simplifies synchronization. Now, multiple producers are trivial to support. We have already done it. You just atomically increment top every time. The old top now points to your private reserved slot of memory, belongs to this thread only, and you use a copy constructor. Of course, you don't use assignment buffer zero memory. Assignment assigns one object to another. In this case, the buffer is zero memory. There are no objects there yet, so you don't assign to it, you copy into it. This is a wait-free operation, at least in what has been so far the normal case, meaning we haven't run out of memory, haven't encountered any other complications. So this is what it looks like for the queue, and the normal case was that top was completely separate from bottom. There was no interaction between them. In the same normal case, let's look at the consumer's point of view of the queue. Initial state of the container, again assuming top and bottom are well separated, is you have some used memory in the middle of the container. In this case, getting elements off of the queue is again very simple. Consumer atomically increments the bottom pointer, and after that, the slot that was pointed to by the old bottom pointer is exclusively owned by that consumer thread. Consumers can start copying data back out to the caller. The second consumer increments the bottom pointer again, starts copying its data back to the caller. These two copies can complete in arbitrary order. Now here you could use assignment because it's really up to the caller what the caller gives you as the destination memory. If it's an already finished object, you can use assignment. Multiple consumers are no harder than multiple producers. Of course, we just atomically increment bottom, fetch the old value. The old bottom slot is reserved to this consumer thread. No problem. Pull the element out to the caller. Call destructor in place. You can't call operator delete because we haven't gotten that memory from operator new, but you can call operator delete on that location. It'll just call destructor, destroy the object, essentially render that what we consider a raw memory. In C++11, you can do both copying and deleting by moving the type out if the type is movable. You still have to call destructor in the end, but if the type is movable, the destructor will have nothing to do. You still have to call the destructor. If the type is movable, it may be cheaper than copying. Dequeue, again, is a wait-free operation. Again, at least in the normal case. What's a normal case? In particular, bottom haven't run into top, and there are a few other exceptions. So we just atomically increment bottom, copy out the elements. This nice, very simple picture holds in the what we consider normal case, which implies that there is more to talk about. Indeed, there is. We will do so after a break. Welcome back. Now time to spoil the fun, or maybe have more fun, because our very simple wait-free queue actually needs to handle a lot of special cases in addition to the normal case for which I have shown you how it works. That's what your queue does. Let's say if your queue is written for high throughput, so it's rarely empty, it does that like 99.9% of the time, but it still has to be correct, if not necessarily fast, in the remaining special rare cases. And what are those special rare cases? Well, there are at least two that you have to always consider. One is empty queue. In our picture here, it manifests itself as the bottom pointer reaching the top pointer. When they point to the same place, queue is empty. Of course, we have concurrency, so we have elements being added by some threads as they're removed by other threads, but one of the threads could see bottom being exactly equal to top, and that means queue is empty. Depending on how you synchronize, you could get into a temporary situation where bottom is larger than top. That also means that queue is empty. It also means you have something odd going on and you have to recover from it. Now, the other thing that could happen, top can reach the end of the block, which means you're running out of capacity. And of course, we still haven't solved the problem of how do we know when the element is ready to be copied out. Producers advance top, but that's when they begin to copy the element, not when they end it. Okay, let's ignore all of that for now, and let's benchmark just the normal case. And why would we do that? The main reason is it's actually going to be hard enough to get those special cases to work. So let's constrain the benchmark so the queue doesn't run out of memory, the queue is never empty, and see if the normal case is fast enough to be worth implementing. Now, what our benchmark is going to do, it's basically going to just atomically advance top and bottom, and producers will advance top and produce, consumers will advance bottom and consume, and we're just going to make sure that bottom never gets close enough to the top by artificially reducing the consumption. So if bottom gets too close, we will stop consuming. We still have to worry about unfinished objects. Right now, we don't have any clue when the object is unfinished. This has to work even in a normal case. Here is one easy solution. Only works if you have exactly one producer and one consumer thread, two different threads. So here is a wait-free queue for two threads. Instead of incrementing top and bottom before copying, you increment them after. So why does it work? If you have only one producer, producer is not in competition with other producers. Producer, for purposes of production, can do a non-atomic increment and doesn't actually have to communicate it back. It can just figure out what top plus one is. So producer knows what top plus one is, and that will be the new top. So producer knows where to construct the new element, right after top in this case. Producer first constructs the element. This would present a synchronization problem if another producer tried to construct the element in the same place, but again, there is only one. And then producer atomically increments top when it finished copying to signal the consumer that the P1 element is now safe to consume. This solves the synchronization problem between producers and consumers at no extra cost. It's still just two atomic increments, just in different order. For the purposes of our partial benchmark, we're going to separate the synchronization cost. Let's measure just how much it costs us to basically do these atomic increments and compare bottom and top. And then separately, we'll worry about how to detect in a thread-safe manner when an object is done copying. So we're going to create this prototype queue. It's not yet a complete queue. That's why we call it prototype queue. Our first version will just be a wait-free, very simple queue where we're doing atomic increments on both top and bottom. We have to constrain the benchmark to avoid running into special cases or at least behaving badly. For example, if you are storing, let's say, integers, you could actually copy out a non-initialized object. You would get out garbage. But if you don't care about that for now, it costs exactly the same to copy garbage integer as to copy a good one. You're just not measuring how much it would cost you to synchronize to never get garbage. Well, here is our very simple atomic wait-free queue. We have some capacity, and we pick it large enough that this benchmark never runs out of memory. We're doing one additional trick with that, which you see in a moment. We just allocate one contiguous block here, and we start from the beginning of the block. To add an element to the queue, we're going to atomically increment the AND, which is our what we call top in the slides. We're going to atomically increment the AND. We're going to take a modulo of it. How does this take a modulo? Well, our capacity happens to be an exact power of 2. By subtracting 1 from this power of 2, I get an integer where, if I look at it in binary, the low bits are set up to the capacity minus 1. So this is I modulo capacity. When AND, which is now locally I here, goes over capacity, it does what an integer overflow would do. It just comes out of the other end. So when AND reaches exactly capacity, this becomes 0. So I'm just looping around this buffer over and over again. And I'm not handling the special case where begin and end actually point to the same element after the modular operation. You would need to handle it, but we'll handle it separately because it has extra cost, and we want to measure the minimum cost. To get an element from the queue, same thing, atomically increment. If bottom reaches the top, begin reaches end, we failed dequeue an element, and our dequeue returns false. If we did not fail, then we take a reference to an object and we assign into it. It means that this has to be an already constructed object, maybe default constructed. what exactly is this a queue of, and what are we comparing with? We're comparing with an STD queue guarded by a spin lock. So we have this header file that contains our data elements. We can vary the size of the data element by varying this pad. We'll begin with just one integer. Other than that, it just has a copy constructor where the just copies the whole memory. Ignore the atomic stuff for now. We'll talk about it later. Right now, it doesn't actually do anything useful yet. We're dealing with the queues of this entry. And we have some test functions. Here are our test functions. On each thread, if the queue is large enough, we're going to consume. If the queue is getting too small, on that thread, we're going to produce. If we fail to produce, and in this case, we cannot fail to produce, but there will be other queues where we can fail to produce, then the test aborts. This queue can never fail to produce. Here, each thread can be either a producer or a consumer, and it alternates, basically depending on how big the queue is. Now, this, of course, is an artificial benchmark, but what it's designed to do, it's designed to load balance producers and consumers to maintain maximum throughput through the queue. It automatically balances the number of producers and the number of consumers to keep the queue size approximately 1,000. So we're measuring in a steady state how fast can we push elements through the queue. And we're going to run this benchmark on one or more threads. And this is our competitor, sort of the baseline, the standard queue protected by a mutex. It's a class which we wrapped. We gave him the same add and get. Now, the reason we have to do this is because look at the interface of the STD queue. It has to check for empty, then it has to read the front element, which doesn't delete it, and then we have to pop the front element. This is not a valid interface for a thread-safe container, even if STDQ was a thread-safe container, which it isn't. So we have to wrap it into interface which provides atomic transactions. So under lock, we do all of these three things. They either succeed or fail. Either it returns false, or if it didn't return false, it will dequeue the first element. That's a queue guarded by a mutex. We're doing the same test on it, and that's exact same queue, but guarded by the spin lock. We have seen spin lock in our earlier chapters. Here is the same thing. Dequeue guarded by spin lock, and in queue or add also guarded by that same spin lock. Compile this one, compile the other one. Runs gives you the values for each, either in queue or dequeue. So it measures the average time to do the transaction. Since we're maintaining constant size, roughly half of them are adding to the queue and half of them are deleting from the queue. Here is our mutex queue and the spin lock queue. You can see that mutex queues right from the get-go considerably longer, but the spin lock queue is actually decently fast, and it's holding its own against our wait-free queue. But remember that the wait-free queue is actually only correct for 2 threads. I was running it for more than 2 threads to see if this synchronization schema is a good foundation to build on. I would need to add more complexity to it to get it to work for more than 2 threads. But do I want to? Well, let's find out. But first, let's have a short break before we go look at the data. Welcome back. We just ran our code, and now we have new fresh data to examine. This is the data obtained on a larger machine with also longer runtime and averaging over multiple runs. The mutex queue is considerably slower. The spin lock queue is faster. Our prototype queue for 1 thread is basically the same as spin lock queue for 2 threads, pretty much the same, maybe a little faster. It is, or it would have been, if it worked, faster for a large number of threads. Unfortunately, we can't have that performance. There is no way to just get this. We have to handle those special cases, because 8 threads would mean that we have multiple producers or multiple consumers or multiple both, and we're not ready for that yet. This is an important lesson. Benchmark your lock-free synchronization protocols as early as you can get them to work, at least partially. Look what we have learned. Even for 2 threads, the spin-locked queue and the wait-free queue show very similar performance here. and the wait-free queue still doesn't handle some of the special cases, it's unlikely that we can get a significant advantage over that spin lock case. If we could, by not too expensive additions, make the wait-free queue work for, let's say, some mid-range 8 threads, that could be worthwhile. So try to benchmark your synchronization protocols early before you add all the special case handling. Just constrain the benchmarks so special cases don't happen. Now, don't take these results as absolute truth. For other workloads on other hardware, you can get somewhat different results, but the general idea would hold. This wait-free queue would be faster on many threads if we could get it to work, but you still need to handle special cases for 2 threads, probably not worth it. Another thing we have learned, maybe to our surprise, that spin lock is surprisingly efficient for very small workloads, where in queuing 1 integer at a time. That, of course, naturally leads us to the question, what if we had larger workloads? Well, remember that array of integers in our entry. We can use it to simulate a larger object. Just pad it to 512 integers, let's say. So now we are enqueuing an object that has the size of 512 integers. Other than that, we're doing the exact same thing. So what do we learn from this? Well, for 2 threads, more or less the same, nothing particularly interesting. But after that, our wait-free queues really gets ahead of everybody else. The spin lock queue shows much lower performance. Of course, the wait-free queue doesn't actually work for a large number of threads, at least not as written. But if we could make it to work, not too expensively, well, there is good potential here. What stops us from getting it to work is the fact that our producers are doing fine. They're doing their atomic increments. We know how to make that work. We have to, of course, make atomic increment of top before we start copying, so other producers don't copy into the same slot. Our consumers are fine. They're doing the same thing. They're doing atomic increment of bottom, and then they start copying. It's the interaction between producers and consumers that we haven't got yet. These interactions take 2 forms. First of all, how to not read queue elements before they're ready, before they're done copying. And second, if you actually deplete the queue completely, bottom becomes equal or greater than top, what do you do then? And we still have to handle that memory case. So our consumers consume, eventually they get all the way to the top, and if they start consuming again, they start reading basically raw memory. That's what we need to avoid. We can try to write a general solution here, and so far, everything I've been telling you basically didn't have any restrictions. We considered one special case, wait-free queue for 2 threads, but other than that, we considered a very general case. It's time to give that up. It's very hard to write a general lock-free queue. It's not impossible, but difficult. Even if you agree to write what's called a bounded queue, which means you never grow that block. Still very hard. What's even more important is that it is unlikely to have good performance compared to the spin locks. On the other hand, typically when you consider writing a lock-free queue, you have some very special case, and you don't need a general queue. You may have only one producer thread, for example. If you take advantage of all of these limitations and all of these constraints, you may end up with a better performing queue. The problem, of course, is that there are hundreds, if not thousands, of these special cases. I can't possibly show you the code for all of them, and showing you the code in detail for one of these very special cases doesn't help you unless you have that special case. So instead, I'm going to show you general solutions for different types of these cases. And then you would have to complete it for your particular application by handling the special cases. Almost always you have this problem of your queue becoming empty. And almost always you will have the problem of your queue becoming full. Let's start with the full queue. Unless you know the maximum number of elements you're going to add, which, by the way, is a possible special case and makes your life a lot easier. So if you know the total number of elements you're going to put in the queue, and it's a manageable size, just allocate that much memory and never worry about it. Let's say you don't. Then the most common solution to this problem is the ring buffer. We have already seen the ring buffer. When top reaches the end of the block, it just loops around. Strictly speaking, it means that your index of top is real top, which is just an unsigned integer, modulo the capacity of the block. You never want to do that. That module is going to be incredibly slow. You always want to set the capacity to be a power of 2 in bytes, and then top bitwise AND capacity -1 gives you the top modular capacity. Your unsigned integer, the real top, the original top, before modulo, will eventually overflow. That's fine. Your modular arithmetic will still work. The same thing for the bottom index. So now these are definitely indices. They're not pointers. They're definitely indices into this chunk of memory used as an array. There are two different kinds of out-of-memory situation. One, we just considered what happens when top reaches the end of the block. You just loop around. But there is another case where you actually filled the whole block. Ring buffer or not, you don't have any empty slots in the block. What do you do then? The most common case is a bounded queue. The producer will fail, and it will return to the caller some error. You have several options. You can do some consumer work on the producer threads, which would lead you to a natural load balancing. You could wait on the producer, so go do something else on those threads, but you can't put anything else into this queue. Unbounded queue, where you actually have to allocate more memory, is much more difficult to write for this case because you're going to be doing an allocation and then you have to switch to the new buffer somehow. You don't want to do a copy of the entire buffer, so you would probably end up pointing consumers to the old buffer until they drain it fully, and then you can free it and new elements getting added in the meanwhile to the new buffer. In order to synchronize it, you would need a global lock. You don't want to have a global lock tested on every call in the normal case. So what you would do is you would use a double check locking, meaning you would have a out of memory flag. If the flag is not set, everything is fine. If the flag is set, that's when you have to take the lock. The easiest solution is to not write unbounded queues. If you need unbounded queue, just use a spin locked queue. Probably not going to be any slower. In general, again, remember that high-performance concurrent data structures get this way. They get their high performance, at least in part, from accepting limitations on their use in payment for that performance. Okay, so how do we solve the other problem? Consumers not reading from the empty queue. The consumers should not read past the top. And in particular, you don't want the bottom pointer to get atomically incremented way over the top pointer, because then it gets hard to recover. Instead of atomic increment, you can use compare and swap. Compare and swap works in two stages. You read the value you're doing swap on. So in this case, you read the bottom pointer. You check if the bottom is less than top. You're getting a snapshot of top at that moment in time. It can go forward, but that's fine. If bottom was less than top now, it will be less than top in the future. Then, if the bottom is less than top, you try to replace bottom by bottom plus 1. You try to do atomic increment, but only if no other consumer has incremented bottom in the meantime. Remember what I just said. If bottom is less than top now, it will remain so in the future. Well, that's not true if another consumer incremented bottom. Then bottom plus 1 may no longer be less than top. So you have to make sure that your consumer was the only consumer for the duration of this entire transaction. And that's what compare and swap does for you. What it also does is it moves us from the domain of wait-free programs into lock-free programs, and those are somewhat more expensive. You could ask at this point, why can't I just read the bottom? If I'm okay, bottom less than top, do atomic increment on the bottom, and then read my element, then I'm fine. The problem is that between reading and your atomic increment, somebody else can do another atomic increment. So now you basically overshot top. So you read the bottom, checked that it's below top, and then another consumer, or maybe multiple consumers, came in and incremented bottom. So now when you increment it, it'll be over the top. Well, you could build in some safety margin. You could check if bottom less than top -1 or top -10. That just reduces your chances of getting a failure. It doesn't eliminate it. If 10 atomic increments happened between you reading and incrementing, you have a problem. There is one special case, of course. That is when you only have one consumer thread. Then you can do a non-atomic read of bottom. Well, atomic read, but no barrier. And then you can take as much time as you want. Nobody is going to increment that bottom until you do. We have already seen this case for our one consumer, one producer wait-free queue. So in general, it will be a lock-free queue. So when you plan your synchronization schemas, always think about atomic transactions. Read the bottom and increment the bottom. That has to be one transaction. Either it's organized as a compare and swap loop, or it's organized as atomic increment, but you can't have it as two separate operations with a gap in between them. So now we're running compare and swap loop on the bottom. Bottom never gets above top, but top isn't really where you can read the elements from. Top is for the producers. It's where they can produce new elements. We still have this trail of partially copied elements lagging behind top. How do we know to not touch them? Well, there are two ways in general. You can have another index like consumer top that somehow the producers would increment when they finish copying the elements. Turns out that this is really hard to do because of the problem that producers can complete their elements out of order. Easier option is for the object itself to signal when it's ready. Let's say our Q element, whatever it is, has an atomic variable in it. And if you don't have any use for it, we will just consider it atomic flag. Let's say in this example, it's a size of some other data that also lives in that object. Then what you would do is you would initialize this entire object except for that atomic flag. And then at the very end of your copy constructor, the last thing you do is you store the true value with the release barrier using atomic store. Until that store happens, the flag was 0. Let's say the object signals itself ready by transitioning from 0 to non-zero. And if you don't have such a natural ready flag, you can just add a member to the object. That's one option. One thing to think about is this initialization here set the size to 0, but that's when the copy constructor started to execute. What was it before the copy constructor was executing? What was it after the producer got this memory for this object, but before the copy constructor started executing? Well, it has to be 0. How do you get it to be 0? Well, when you first get the buffer, you just initialize the whole buffer to 0, then it's 0. If you're using a ring buffer, you'll go around the second time. So how do you make sure it's still 0? The destructor sets it back to 0. Just like here, the destructor sets it back to 0, so this really isn't necessary. It has to be 0 even before the copy constructor. Okay, let's take a short break, and then we'll go back to the code and see how these atomic flags are actually implemented and used. Welcome back. Let's see the code of a queue implementing synchronization by in-object atomic flag. We can look at the code. In particular, we can now recognize the mystery of this atomic flag. Here is your copy constructor. It sets the value of whatever you're reading. First, it reads it, and it's copying it from the right-hand side in this case. So it reads it, and then it stores it with a release barrier. Assignment operator, if you need it, would have to do something very similar. As we have seen in the plots, we have two sizes of this thing. We have large object here padded to, in this case, it was 1024 integers. In the benchmark I ran for you in the table, it was 512 integers. Either way, you first copy the pad, which in our case emulates copying the data, and then you reset the size, which we just call x, because it's not really, the size is static here. But you reset the flag. In our example on the slides, the flag doubled as a size. That was just a happy coincidence. For the purposes of the queue synchronization, what's important is this atomic flag. The fact that you can reuse it as a size was just our luck. So let's see how it works with the synchronization. Here is our new concurrent queue. Again, it has a block of capacity. Again, we will be using the modular arithmetic. Adding is very simple, still wait free, because the producers, they just increment the top and construct new element in memory. We're not actually handling the case where the queue is full yet. So this is a prototype queue. This is not finished queue. We're just measuring the cost of this additional synchronization that we just talked about, which is the synchronization on the consumer end. So we still have some more special cases to handle if we wanted to proceed implementing this. Before we do that, let's measure if it's worth doing. The changes from our previous queue are all in here. First of all, this is our compare and swap loop. We load the begin, the bottom, and then if it hasn't changed, we're going to increment it atomically using compare exchange strong, which is the C++ way of saying compare and swap. While we're considering whether to increment it or not, we will check if the queue is empty. If begin reached top, and will return false. We will also look at this element that we're about to consume. Atomically load its flag, and if it's 0, then we will refuse to enqueue. If we successfully incremented the value of begin, now we actually own the old slot and we can copy the memory out. The special case for queue filling up manifests itself that while this is the only consumer that can get to the slot, the producer can actually come all the way around and write into the slot. That would be the queue getting close to full. So we don't handle that yet. That would need to be handled separately if we decide to proceed with this implementation. Let's benchmark it. Takes considerably longer because we have more bytes to copy, but actually goes faster as we have more threads because those threads are copying bytes in parallel. The same thing with the spin-locked queue. Doesn't scale quite as well. So let's look at more statistically reliable data. If you run a longer benchmark, this is what the data for the 512 integers would look like. So the mutex is way, way slower. The spin lock and our prototype queue version 5 in this case, because there are a few other versions that I didn't show you that did some partial implementation of the synchronization protocol. They're just not worth considering. Here we see that for large number of threads, it pulls ahead, but only for this large object. For the small object, when we're copying one long, you can see that it's actually a very bad queue. Why is there such a difference between small object, where spin lock is by far the best, no competition, and large object, where spin lock isn't actually doing all that well, and the lock-free queue is doing much better for large number of threads? The reason is in the size of the critical section. When you put a lock around stdq, you put a lock around the entire pushback in this case, or pushes on the queue, just a wrapper around pushback, including copying the data. Not just allocating new slot for the new front of the queue, but also copying the bits happens under the lock. The larger the object, the more bits you have to copy, the longer it takes. And you're doing it all under lock, so it's all done one thread at a time. Our lock-free queue has the protocol that does some synchronization on the bottom and top indices, but after that, the thread that wants to copy gets to copy its bits without any further abstraction. In particular, our compare and swap loop just reserves the slot at the beginning of the queue for the consumer thread to copy out. That's why, as we get bigger objects, the cost of copying under lock eventually overwhelms the locked queues. Now that we understand this, of course, the natural question is, can we do the copying outside of the critical section, but still use the locks? Why did it happen to be this way in the first place? Well, this was actually the natural way to write log-based code. You have your stdq or your other just regular queue, and you put a lock on the entire push or enqueue call. That call inside has the copy. You don't have to write it this way, but if you just go putting locks around the container, that's the natural way to do it. In order for us to do better, we would have to put a lock around just the portion where we allocate the new element, where we reserve the new element, but not where we copy it. You can't do it with the stdq directly because you can't stick your locks inside the push method. You would have to basically write your own and put the locks inside. But is there a way to do it just with an stdq? And the answer is yes, there is. Now we get to what's called sometimes minimally locking queues. They were all the rage 20 years ago. By now, I guess they became commonplace. They're basically queues of pointers. You allocate the memory for the new element. You copy the value, the bits of the object, all outside the critical section. And then when you're done allocating and copying, under the lock, you insert that new node into the queue. Memory allocation may have its own lock, so that could limit your scaling, but it's particularly good if you actually don't need to do any allocation or copying. Let's say your client, your caller, already has these queue elements allocated and stored in some memory and doesn't actually want them particularly to be copied elsewhere. Your normal stdq will copy them if you use it on that element, but that's not the goal, let's say. You would be perfectly happy to keep them where they are. You just want to establish the order in which they're processed, and that's a queue order. In this case, you can enqueue and dequeue pointers to these elements. Then you don't have any copying at all. and your critical section just became so much shorter. Of course, not only can you learn to write better locking code by considering some lock-free ideas and stealing them, the reverse is also true. Now that we had this idea from minimally locking queue about the pointers, we can also apply it to our lock-free queues. Because one of the problems we had is how to know when an object is ready to be consumed. When the pointer atomically changes from null to a valid pointer, that's when it's ready to be consumed. And while the pointer was null, it wasn't pointing to anything, so there wasn't anything to consume. Easy and elegant solution. How fast would that be? Well, we have just seen a queue for enqueuing 64-bit longs. For the pointer, it'll be exactly the same thing. So it's fast, but not excitingly fast compared to a good spin lock. As any other software problem, we just solved ours by another level of indirection. This is how it looks like. We have this queue of pointers. So our queue conceptually enqueues elements of type T, but what the queue really enqueues is T star. And the slots that aren't ready yet just have null pointers, including the slots that are in the process of becoming ready. They atomically change from null to not null. And then, of course, we have some other data structure which holds the objects, could very well be client's data. In general, minimize the duration of the locking section. Always think about what has to be done under lock and what actually operates on thread-specific data and doesn't need to be done under lock for any reason other than we haven't thought about it. Let's have a short break on this note, and then I will show you another very interesting queue that approaches the same issue of minimizing the duration of the critical section, but from a totally different point of view. Welcome back. As I promised, let's see yet another way of minimizing what's done under lock, totally unlike what we have seen before. Now that we're talking about making smaller critical section, here is another idea for you to consider. If you remember, the spin lock, in addition to lock and unlock, mutex for that matter too, has this try lock member function. What that does is it tells you if you did lock, would it block or not? If it wouldn't block, it actually takes the lock. So if lock succeeds, try lock is a lock. But if lock would have failed and blocked and you would have waited, try lock instead returns false, returns some error code. So when you call try lock, you either get the lock or you immediately get back a value that tells you that you didn't get the lock. Well, how can we use it? Here is an interesting cue for you. We begin with an array of atomic pointers to single-threaded queues, could be STD queues. We use these arrays we use each pointer in this array basically as a spin lock. But we're not going to spin on it. We're just going to try it once. And if we didn't get the first one, we're going to move to the second element in the array, then the third one, and so on. And if we get to the end, we'll start all over again, and we'll keep doing that until we find one of these atomic pointers that points to a queue that nobody is using at this very moment. Remember that try lock is atomic in the sense that it either gets you the lock or returns a failure code. You're not asking, could I get a lock, then trying to get the lock, because by that time, maybe you can't. If you succeed, it's atomic. It returns the code that says you succeeded, and you know that you got the lock. So we're going to basically scroll along this array until we get a single-threaded queue in our exclusive ownership. Why exclusive? Well, because we just try-locked the only pointer to that queue. Then, since it's exclusive ownership, we are safe knowing that this single-threaded queue is only accessed by one thread, the current thread that locked the lock, and we can proceed to enqueue or dequeue. This is how it works. Implementation-wise, you would typically grab it by an atomic exchange. So you atomically exchange these Q star pointers with null. If an array element has null in it, then this single-threaded queue is taken, owned by somebody else, go to the next one. If it's not null, well, atomic exchange just made it null, and you own the queue. What's in the single-threaded queue? Well, we can do an STD queue, or we can just have a ring buffer. Ring buffers are very easy if they can be operated on only one thread at a time. You don't need any atomics in them. Very simple. Now, ring buffers can fill up. So if that's what you're doing, there is a possibility that your queue will fail to push, and your interface has to handle that. Pushback on an STD queue just never fails. It can throw out memory exception, but it doesn't refuse to enqueue. On our queue, it could. Let's look at this try lock based queue. As I said, there are two versions. In the first one, our single-threaded queue is just a ring buffer. So here is our ring buffer of capacity. In this case, we don't have to worry about anything being atomic, so we can just roll over the end of the buffer easily in any way we want. As you see, nothing here is atomic. Here is our atomic pointer, and look at this padding here on all x86 machines. Cache lines are 64 bytes. So what I have done is made sure that the atomic pointers are all on different cache lines. And the reason is accessing from two threads to different values that are not technically shared, but they are on the same cache line, is exactly as slow as accessing the same shared value. That's called false sharing. We have seen that in other chapters of this class. So this avoids false sharing. Now here is our concurrent queue. We have an array of these queue pointers. Each of them has an atomic pointer to a single-threaded queue and the padding. And here is an in-queue and dequeue. Let's see how they're done. So we have a slot for, let's say, dequeuing, dequeue index. We atomically increment it. This one, here we use the modular arithmetic to roll it back inside the array. So this is just modulo queue count. We atomically exchange that queue pointer with null. So there are two possibilities after we do the atomic exchange. The first one, we got the queue, and we can pull the front element from it, if it's not empty. So could be empty. The single-threaded queue could have nothing in it, and in that case, we fail. But if we succeeded, we copy the element out. If we fail to get a queue, there is still a possibility that the entire queue is empty. There is just nothing to get. In this case, looping over the queue would be pointless. And we don't actually know whether the entire queue is empty because we only can look at one of these sub-queues at a time. To solve that problem, we have to maintain the atomic count of elements in the queue. And here we're loading it and checking if it's 0. So this is for the entire queue. That's why it's atomic. And if we have to spin on the array, we have to do a little sleep. Otherwise, we have seen it for spin locks. If you keep hammering the spin lock over and over without any interruptions, basically that thread gets more and more compute time, and you want the thread that wants to release the spin lock to get more compute time. If you successfully fetched an entry, then we decrement the count here atomically. But where was the count incremented? Well, here is our enqueue. Begin by adding 1 to the count. We take ownership of a sub-queue in a similar fashion. We have enqueue index, which we atomically increment, try to get that queue by atomic exchange of the pointer. If we got it, put the entry in, the queue could be empty. If it's not empty, we store and return success. If we failed to get an element from the queue, we have to sleep, and then we again go to the next enqueue slot, which we incremented on the previous run. So we keep trying enqueue slots one after the other. Enqueue slots and dequeue slots are just indices into this array. So why don't we just start from 0 every time? Well, we could. The problem is you would have higher contention because all threads that come in would start from 0. One of them would get slot 0. The next one would probably get slot 1, and so on. So instead, we kind of disperse it. So we remember the last slot that was enqueued successfully, and next time we start from the next one. So we have a round robin going, and the same for dequeuing. Instead of using these simple ring buffer queues, we can actually use an STD queue with the same array of atomic pointers inside our concurrent queue class. So here is atomic pointer to STD queue padded to the cache line. We're dequeuing, incrementing the slot, doing atomic exchange. If we didn't get back null, if we got a valid pointer, there's null there now. So now we have exclusive lock on that queue, check if it's empty, pop the element. Well, if it's empty, we have to release the lock. Well, we always have to release the lock, but if it's empty, we have nothing to do other than release the lock. We don't pop anything. We check for the global count. If it's 0, that's it, the global queue is empty. If it's not 0, we'll try the next element in the array. Maybe that queue is not empty. If we failed to acquire the lock, so we did atomic exchange with null, and we got back null, which means it already was null. Somebody else is holding the lock. Again, we have to check the overall count. Makes no sense to keep spinning on the array if there is no elements in the entire queue and nothing else is coming. Maybe all the producers stopped. And we keep spinning in this incrementing the queue slot in this loop. This is our loop where we spin over the array. We have to periodically check for the count. Same as the ring buffer, only it's a little bit simpler because we don't have to check for out of memory case for the enqueue. Here is our enqueuing, here is the loop. Increment the enqueuing index, try to get the log. This works like a try log. If you get back not null, it means you successfully took the log, you own it, and furthermore, you got back the signal that you successfully owned the log, you got a non-null value here. If you get back null, you failed to acquire the log, but you're not waiting on anything. You just get back the signal that you failed to acquire the log. So here is our enqueuing, because enqueuing on an STD queue cannot fail. This is much simpler. Push the new entry into our single-threaded locked queue, release the log. This relinquishes the ownership. It stores the old value back into the array. So now some other thread can get it, return that we succeeded. And until that happens, keep spinning and sleep. Other than that, stdq has exact same structure. So here is our global count. When we add, we increment it. When we remove elements from the queue, we decrement it. That's so we know that the consumers shouldn't just keep spinning forever. Our enqueue slot and our dequeue slot, again, we don't start from 0 to avoid contention on the beginning of this array of queue pointers. The benchmark is exactly the same. We're going to run the same test fixture, only it will be on this concurrent queue. We're ready to run this code, but reading it and commenting on it took a bit of effort. So let's have a short break. When you come back, it'll be ready to run. Welcome back. We spent the last section exploring the trilog-based concurrent queue. Now it's time to see how fast it is. And you can see that this actually scales quite nicely. It becomes faster as you add more threads, which is what you expect from a well-scaling program. Of course, we don't have 128 different processors on this machine. We only have 4 with hyperthreading, so maybe 8. If you're willing to count hyperthreading, looks like we're getting some benefit from the hyperthreading. But definitely at 16, we're just running 2 threads per CPU, so there is no more hardware to use here. This is all just overhead of competing for the same hardware. Not so in the graph that I'm about to show you on a larger machine, longer run. Let's go see that. Everything's thrown together. Mutex doesn't need to apply. Spin lock, pretty good until we reach to the large number of threads. Our prototype queue is down here at the bottom. Again, decent. Our trilog queues are now here. The trilog queue on stdq, which is these triangles here, similar to spin lock, then becomes faster at a large number of threads, a little slower than our lock-free compare and swap prototype queue. But remember that that one wasn't finished yet. We haven't handled all the special conditions, so there is a cost there. This crosses down here. Here is our trilog queue on the ring buffer, which is actually a more fair comparison to the prototype queue because that one also has a ring buffer and can fill up. The trilog queue on stdq has the same advantage as stdq. It can never fill up. It's unbounded queue. A more fair comparison is these two lines here, the lock-free queue versus the trilog bounded queue. And you can see that basically it pretty much never makes sense to complete our lock-free prototype, at least under the conditions for which it was designed. Multiple producers, multiple consumers, bounded queue, signaling object read in the object. You could have more restricted conditions, then it would go faster. There is, however, another reason why you might still want to finish the lock-free queue. That reason is we did have to give up something when we wrote the trilog queue, just like we had to give up something when we wrote the lock-free queue. And that is your elements don't always come out in the right order. Why don't they come out in the right order? Well, you have 2 threads trying to push. They will get 2 different single-threaded queues from the array because you can't get the same one at the same time. And you do a loop around the array, so one of them will grab one element from the array, then the other one will have to go grab the next one. There is no way to know which of these 2 slots in the array will be inspected first when the time comes to dequeue those 2 elements. So you could end up getting the element that was enqueued later to come out first. Is this bad? Well, it sounds like it's very bad because the queue is a data collection in which the items are kept in the order in which they were inserted, and primary operations are in queue and dequeue, and queue inserts the item and dequeue removes them in the order in which they were inserted. I just told you that this concurrent queue does not necessarily remove them in the order in which they were inserted. How much of the problem is it? Let's think about some arbitrary concurrent queue. Here is some generic concurrent queue. It's a conceptual picture. We are looking at it as a sequence. Of course, there is no way to actually look at the whole sequence through the queue API, but let's say we attach the debugger and look at what it looks like right now. And we have this sequence, and the element 1 is at the front of the queue. So we're going to call dequeue twice. We expect 1 to be dequeued first and then 2. We're also trying to enqueue 13 and 14. And let's say 13 gets enqueued faster. So 13 will go into that slot marked by the question mark, and 14 will be after it. Then we would expect 13 to eventually come out before 14. Let's remember that this is a concurrent queue and look in more details at how this is happening. So now we have two threads, both doing their enqueuing and dequeuing. Let's look at dequeuing first. Before you can ask what happened first, you have to define first. If the two threads are just calling dequeue at the same time and you didn't establish any relative order, you don't know in which order they happened. In particular, what could happen to you is, let's say there is still that array inside. So the thing about our trilog queue is it didn't have such an array. But let's say we're looking at a queue that does have an array, and we stopped it under debugger and we expected the memory, and it goes in this order, 1, then 2. Here is our pop front. Pop front will get the first element. We know that 1 is the first element, so the first call to pop front will get 1. And the second call to pop front will get 2. And then it's running on two separate threads. It has to return to the caller. There is no guarantee that one of the threads will not just decide to take a short nap between the x equals statement and the return statement. So even though this statement got element 1 first, you may get a return to the caller from the thread that got 2. So then from the client's point of view, it's as if 2 was dequeued first, because client only knows which pop around finished first. So client, let's say you just print them. When you got the elements, you print them. And it's entirely possible that even in this picture, when 1 was definitely in the queue before 2, thread 2 finished its return statement first, so you print 2, and then you print 1. The very same thing can happen on the back end of the queue. Again, in order to define first, you have to know what happens before, what happens after. If you don't know what happens before, what happens after, then what could happen is thread 1 calls in queue of 13, and that happens first. Everybody agrees that it happens first. Let's say you print it when you call it, and you print it in queue 13. Here is your pushback, which is what sits inside in queue. Element 13 on thread 1 passed through this boundary first. And then thread 1 was delayed, was interrupted. Thread 2 runs ahead, and this assignment happens on thread 2 first, so 14 goes into this slot before 13. Entirely possible. As I said, in order for you to actually know what's first and what's second, you have to define some kind of order. There are several ways you can define order. In particular, you could say that if x and y were enqueued by two different threads, I really don't know anything. But if x and y were enqueued by the same thread, then I do know which finished first. There is no question about it. And I would like at least those two to come out in the right order. Now, if x and y come out on different threads, then you don't actually know whether they came out in the right order because the return to the caller may be delayed. But let's say x and y were also dequeued by the same thread. Okay, then there is no question about which dequeue finished first, and I still want x to come before y under these limited conditions. That's one case where you actually know the order. Another case is, let's say I did pushback x and it completed. And I know that it completed, maybe I printed something, maybe I took a log, but it completed before pushback y was even started. If pushback y and x were started at the same time or with overlap, then I don't know what was happening inside them. I don't know who actually finished first. But if pushback x was completed before pushback y was started, then I know for sure that x was enqueued first. And that's true whether it's on one thread or on multiple threads. Now I would like x to come out first, but how would I know what's first? Let's say I call pop front and I get X, and I wait until that pop front completes, and only then I call another pop front, and that one should give me Y. The reverse order should not be possible. These two ordering guarantees are, at least in theory, possible. You could establish them. I'm going to be somewhat less than formal now when I say that these two guarantees together define the property called sequential consistency. It has a formal definition that you can look up for our practical purposes. This is what it means. If you have both of these guarantees, then you have what's called sequential consistency. So, do you care about whether or not your program has sequential consistency? Sometimes you do and sometimes you don't. Why would you not care? Well, let's look at the first guarantee. X and Y are enqueued by one thread, and they have to be also dequeued by one thread. Different thread, but one thread. How likely is that to happen? It may be important to you that if it happens, they come out in the right order. But usually, if you're not counting on them being dequeued by one thread, you just don't care. For the other one, well, you could definitely establish the order. You could call one pushback on a thread, then wait for that to complete, then call pushback on another thread. You can do that, and you just fully serialized your program. You don't actually need a high-performance concurrent queue because you're calling one pushback at a time. A queue with a lock around it will do exactly what you want, call one pushback at a time, and it's much simpler. So if that's what you want, just take a queue with a lock on it. So my point isn't that sequential consistency has no value. Quite the opposite. Sometimes it has value. My point is that there are many cases where you don't care. And you don't care because it would be very expensive, not just for the queue, for the design of the program. Like you would have to put the serialization barriers between different pushbacks to know what happens before, what happens after. If you have a program that needs that kind of serialization, it will probably scale poorly. Probably, not always. Another advantage is a sequentially consistent program is much easier to understand, much easier to reason about, and much easier to debug. If you don't care about sequential consistency, which means you don't actually go to great lengths to establish this additional order, whether or not you use a trilog queue or some other queue, in your program, what you see is a queue-like order. Most of the time, first in, first out, mostly. And if that's what you need, then you should consider giving up sequential consistency as a trade-off for performance. As always, with these subtle high-performance concurrent data structures, you have to know what you're doing. Don't give up something you absolutely can't live without. But non-sequentially consistent data structures can be faster, as we have seen on the example of this queue. This trilog queue with a ring buffer was a little bit faster than a lock-free queue with a ring buffer, and the lock-free queue wasn't actually finished yet. The amount of code to finish it depends on exactly which special case you want to handle, but it's probably like 5 times more than what we already had to implement the normal case. Whereas our trilog-based queue was actually complete. What I showed you, that's it. What I had on screen is what you need. It was working perfectly for all cases. So it's much simpler, it has superior performance, and all you had to give up was sequential consistency, which means it's really hard to debug. That's why you test it. That's it for our queues. We have seen all sorts of lock-free and wait-free prototype queues, kind of skeletons you have to put flesh on if you want to implement queues for some particular special case. Don't bother implementing a lock-free queue for a general case. We have also seen some worthy competition to these lock-free queues in the form of spin-lock-based queue. Just remember to have minimal critical section. Pull the copying of bits outside of the critical section. And in particular, the trilog queue, which actually always has the copying of bits outside of critical section, because while one thread is doing the copying into one single-threaded queue, another thread is free to go ahead and access next element of the array with its single-threaded queue. So the critical section is really, really small there. I told you that the trilog queue, as a price for its high performance, gives up sequential consistency, which manifests itself as returning elements out of order, which is different than sequentially consistent queue, which pulls elements in the correct order and then just fails to return them. Can you write a program that actually spots that difference? You would have to hit those two guarantees that I was talking about. Remember that actually catching this trilog queue in the act of returning elements out of order is somewhat a matter of luck. We know that it can. If you write the synchronization of your enqueues and dequeues correctly around it, you should be able to catch it in doing so, but you still have to have the luck on your side. Your luck can be improved if you have more CPUs because just more different things happening at the same time. See if you can spot violation of sequential consistency. That's it for our queues and block containers in general. Stacks and other block containers are written in a very similar manner, have fundamentally similar performance, which is the more general it is, the less likely it is to have superior performance. The more special conditions you can accept for your unique application, the better your odds are of actually getting something worth implementing. Welcome to the next chapter of our class on high-performance computing in C++, where we'll take a more general look at performance, and I'll sketch a path for you from the simple, concrete, specific examples that we studied for most of this class to more general ways to improve performance in your actual programs. The examples, well, some of them may be useful for you in your work, but mostly they are learning examples that we studied in details that gave you the understanding and the tools and the knowledge necessary to apply to your daily work to get a similar level of understanding of what controls performance and how to improve it for whatever algorithm and data structure you may be working on. So how do you go from specific data structures and from specific locks and other individual little details to the performance of the entire program? First of all, you have to focus your efforts. Reaching maximum performance will come as a constraint on your implementation and as a trade-off, at least against code complexity, development time, possibly against maintainability, portability, if you have to do something hardware specific. It's not free, and it's a resource that you shouldn't squander. You should apply it judiciously, just like any other finite resource. If you have either a third party or in your own organization a library of high performance algorithms and data structures, or if you take time to generalize somewhat what you work on and eventually build up such library from the pieces you had to write for your work, you can pay it forward and have a library that you can then use as foundation of your program. In a sense, you get a free performance later because you have these high-performing data structures. Even if you do that, typically the most demanding portions of your code will benefit from one-off solutions. For example, we have seen in other parts of the code an atomic shared pointer, which is a fairly good data structure, and certainly a lot of effort went into optimizing it. And yet, for a specific application, a pointer in a list, a trimmed down version of this generic data structure was able to outperform the atomic shared pointer. Now, whether it was worth our while to write a specific pointer for a list or just use shared pointer from C++, that depends on how much performance of that list matters to you. But in the most demanding cases, you will need application-specific, problem-specific solutions. So what we did in this class, we have to start somewhere and you can't start from everything at once. So we took a look at building blocks of high-performance software. Individual data structures for which we considered a few examples, different ways of locking and synchronizing access to shared data and shared data structures. And that was as much, perhaps more, for learning and for teaching you how to understand these things than for the examples themselves. As you apply these skills to other algorithms, other data structures that you work on, you end up with a set of building blocks. Good building blocks do help you make better software. You still have to use them right. So now let's take a broader look at what it means to have good performance and how you work toward achieving it. First of all, you have to keep in mind what good performance is actually application dependent. If you switch domains, you become very acutely aware of it. What was critically important for high performance work on supercomputers doesn't really matter if you switch to developing for cell phones. And we'll touch on that in a moment. Also, what you learn in theory, of course, has a bearing on practical results. An algorithm that is n-cube complexity is always going to have that bad performance hanging over it there's nothing you can do about it. But there are practical considerations that are not readily visible when you just read about computational theory. And a lot of these come from combining things that are simple individually and building larger systems. Many practical factors you have to consider. Let's look at some of the ones I named just to point out how large they can be and that you should be aware of. Let's start with this theory versus practice thing. Here is a definition of the wait-free programs. Each thread will complete its task in a finite number of steps. Doesn't matter what other threads do, all threads at all times make progress toward the final result. Looking at this definition, you expect good scaling. For example, let's say you have n steps to complete for the total work to be done. If there are n steps to complete and all threads are always making progress, they'll do n over 2 steps each and the work is done. So that would be twice as fast. And 4 threads would be 4 times as fast and so on. Now, if we switch to log-free programs, where at least one thread is making progress at all times, we can assume that in the worst possible case, if always one thread is making progress, those n steps will be done sequentially by any number of threads, possibly one of them, the one that's making progress, or it will be spread between different ones, but at any time, in the worst case, one thread is making progress. Now, that's the worst case, so no scaling n steps serially. We hope for a better scaling, of course, where more than one thread is making progress most of the time. So let's put this theory to the test. The work will be incrementing an integer n times. That's a stupid way to compute a sum if sum is what you need. Let's assume that what you actually need is some sort of shared counter and you actually need to know at all times what the value is, so it has to be synchronized between different threads. So the wait-free way to increment an integer n times is to have an atomic integer and increment it. That's once, and you do it n times, that's n times. The log-free way is with a compare and swap loop. Given that you have an atomic increment, you would never actually do such a compare and swap loop just to increment an integer, but bear with me, let's see how those theoretical definitions and the scaling we predict from them, how they bear out. Based on the definition, this is what we expect. For ideal scaling, which is what we expect in case of wait-free, whatever time it takes to do on one thread, it will be half of the time on 2 threads and so on. If there is no scaling, and we expect better than that on log-free, but that should be the ceiling. The worst case, n steps all done one at a time. The same time that it takes to do on one thread, it will take to do on 2 threads and so on. So no scaling. We expect you can never get better than the blue line, but we expect wait-free to be close to that, and log-free somewhere in between. This is what we actually get. We've done the test. I've shown you the code in another chapter of this class. So this is the data. First of all, wait-free is, that's the bottom line, the atomic increment, nowhere close to ideal scaling. In fact, it actually becomes worse with the increasing number of threads. So not only it doesn't scale, it has extra overhead. Log-free, that's the top line, it has more overhead. Going back to this definition, remember that what we said was each thread is making progress and each thread will do finite number of steps. What it doesn't say is that the step should always take the same time. Naively from this definition, we could expect that, okay, step would be an increment in our case. So however long it takes to increment, n times that, that's our steps. Well, that's true, but apparently it takes longer to do individual step, to do an increment, if you have other threads trying to do the same. So in hardware, there is waiting. It's a wait-free program from the program point of view. The program is written without any explicit delays. But the action of increment actually is not free from wait, and the hardware waits on the concurrent increment done by another thread before doing your increment, the one you're trying to do on the thread you're watching. All threads do make progress in the sense that you don't see any branches in the code that come back. You're just doing increment, increment, increment. There is no code that discards the results, that aborts computation, but they don't make progress at the same rate. And all of these corrections, on one hand, they're purely practical. The theory has nothing to say about how long a step takes. On the other hand, they're ultimately important to you because what you care about is how long the program runs. So if all threads make progress but much slower, well, that is something you would like to know. The real-time cost of step or the real-time pace of progress is affected by a lot of practical implementation dependent things. Now we're talking about the real time as the ultimate performance metric, and that's true as long as you live in this HPC, high performance computing domain, where you care about throughput usually. Throughput is basically the amount of work you can do per unit of time, or the time it takes you to do a given work if you have a fixed work. In some cases, you worry about computations per watt of power if you're also concerned with the cost of running a large data center, but for the most part in HPC, we worry about throughput. That's by far not universal consideration. For example, if you live in a mobile or embedded world, power use may be more important than throughput. You don't want your cell phone to be too slow, but if it drains the battery too fast, that's a killer for your practical use, for your success in the market. So power use is ultimately more important. Real-time systems, again, some embedded systems, sound processing, video processing systems, for them, yeah, they may care about throughput. Some of them do a lot of computing, such as compressing and decompressing video. But once they have enough power to do the computing, what becomes critical is the latency. If you have a long latency tail, occasionally your audio starts to stutter. That metric is, for the most part, entirely absent in HPC considerations. You don't actually care how clumpy your computations were, as long as the result is given fast. In real time, beyond certain speed, it doesn't do you any good to compute faster, but you do want to compute just in time, always. Let's go back to our demo problem of incrementing an integer. The only reason I'm choosing it is not because it's unique, it's because it's simple. It's free from almost any sort of additional complication that you might try to blame for the variety of results that you see. There's very little extra going on here. So let's say we have some integer that we want to increment. Let's make it slightly more realistic. Our integer is a part of some larger data structure. We have a pointer to that data structure. And we have our wait free, which is atomic increment, which in C++ you can do just plus, or you can call fetch add. We have our lock free, which is compare and swap, in C++ compare exchange. And we add spin lock. It has a lock interface, so you call lock and unlock on it. It basically has an atomic flag that you're spinning on. If you do that, then the integer itself n does not need to be atomic anymore. And we have seen in another chapter of this class a pointer spin lock, where instead of atomic flag, we use atomic pointer. So the pointer plays two roles. It points to the data, and it's used as atomic flag. This way, we, instead of accessing two independent variables, we only have to access one. The way that spin lock works is you exchange atomically this pointer with null, and you keep the local copy. That's what exchange does. Then you use the local copy to access the data structure. Nobody else can get to the data structure, so n doesn't need to be atomic. And then you put the pointer back, and this enables some other thread to get to the data structure. Well, this is our HPC view. Lock-free is slower. On this machine, spin lock is slightly faster than atomic, but in general, they're kind of similar. On a different hardware, spin lock could be slower. But this is the mobile view. I don't have a way to measure power, but CPU time is a good proxy for power use. Here I have put mutex, which is just another kind of lock. It's not a spin lock, it's the pthread mutex. Compare and swap, and you can't actually see the spin lock line. It's right under the pointer spin lock line, so they're both very low CPU time. But this is a logarithmic scale, so the differences are actually even larger than for the real time, for the throughput view. If you are in a real-time, low-latency world, then latency tail is the most important performance aspect to you. So here is a plot which shows, for the same increment, deviation from the average time it takes to do the increment in percents at 95th percentile. At 16 threads for the atomic increment, 5% of increments take more than 105% of average. So 0 is average. This is 5% higher than average, and that's where 95th percentile is. 5% of all increments are even longer. Mutex, in this case, has pretty long tails, 45% deviation at 95th percentile. So to get 95th percentile of all increments, we have to be up to 145% of average time it takes to do an increment. Now, this is a particular piece of hardware, and it's not a low latency system. So don't take any specific lessons from this, that mutex is always better, or log-free is always worse, and so on. But take it as a precaution that different log-free synchronization schemas, even the ones that may be very fast, they are fast on average, but possibly not necessarily fast in the sense of a long tail of the distribution. For your low latency hardware and OS, you have to measure what gives you the best latency distribution, and it may not be the one that gives you the best throughput. So you have to be aware what performance means for you, and you have to be aware of it when you optimize, but also when you use high performance libraries or high performance algorithms. They're not necessarily high performance in the sense that you're using the word in. Although if you're in HPC world, typically that's what they do. So if you are in low power world, you may find that they are high performance, but also high power. Okay, let's take a short break now, and when we come back, we'll look at different factors that contribute to performance of large programs and how you go about analyzing them. Let's look now at what contributes to performance of real-life programs and how can you detect it, improve it. So there are a lot of factors in general for any concurrent program, and concurrency is what we were focusing on throughout this class. At the high level, it's available parallelism of computations and data, and the granularity of parallelism. That mostly depends on your algorithm and the organization of data. Then, kind of as you go toward lower level, you run into the critically important amount and frequency of data sharing. As we have seen before, as far as concurrency and performance is concerned, data sharing is the root of all evil. The amount of data sharing and how often you have to access shared data has critical effect on the efficiency of your concurrency and therefore on the performance. At the implementation level, at the lower level, which is where most of this class have been, we have looked at different synchronization schemas, which of course are only necessary if you have something to synchronize, which means you have shared data. If you didn't have shared data, life would have been very easy. So you have shared data, you have to synchronize access. We have also touched on the issue of the overhead of this synchronization and the cost of data sharing, and that's something I want to give you a summary of right now. All of these factors are not entirely independent. Of course, your choice of algorithm determines what's available for parallelization, but also it may determine how often you have to touch shared data. On the other hand, if you have access to a better synchronization scheme or a lower overhead synchronization, you could make parallel some computations that were not parallel before in the same algorithm, simply because you can do cheaper parallelism. Let's look at a queue example just so I have something to point to when I talk about data sharing. So we have a queue, and we can do a very simple log-based queue where, for example, we can take C++ std_queue and wrap push and pop into a log. Or we can take a log-free queue. It requires a certain synchronization protocol. There are many options. Here is one. For push, you just atomically increment the top pointer and at the same time fetch the old value of the top pointer. That's all atomic in one instruction. If you do it atomically, then on each thread, once you got the value of the old top pointer, no other thread can see the same value, since increment and fetch are atomic. This means that the producers are actually wait-free. The producers are the ones doing the push. Consumers, that's the threads that are doing the pop. Well, they just increment the bottom pointer and get the slot, but they have additional constraint. They should not attempt to reach past the top. They should not try to read the queue slots that haven't been initialized yet. And that requires that instead of just plain atomic increment, you have to use compare and swap. And within the compare and swap loop, you have to check if bottom overshot top. And if bottom overshot top, then you don't swap. If bottom is still below top, then you can try to replace bottom by bottom plus 1 by the next slot, and you only do that if another consumer haven't incremented bottom yet. That's why you can't use atomic increment, because there is no way to test whether bottom overshot top inside the atomic increment. There is no inside. Atomic increment is atomic. Whereas compare and swap loop, you can get the old value, check if you want to increment it, if bottom is less than top, and if you do want to increment it, try to increment it if bottom hasn't changed. So that means that consumers are lock-free, but not wait-free. Finally, we have to avoid reading data that is currently being copied in by the push. So pop, in addition to staying safely below the top pointer, you also cannot consume data that hasn't been produced yet. And one of the ways to do this is to have this atomic ready flag inside every element of the queue. And when you copy the data, the last thing you do is you set the value of the flag. Let's say in this case, it's maybe you set it to the size of the data, or you could just change it from 0 to 1 if all it is a flag. And that signals to the consumers that this queue element is ready to be consumed. That's wait-free. The consumers don't have to run another compare and swap loop for that. You have seen the code in the chapter of the class that is dedicated to lock-free queues, but here is the performance measurement. For a small queue element, 8 bytes, the spin-locked queue performs much better than a lock-free queue. And for a large queue element, let's say kilobyte, a spin-lock queue performs much worse, especially at large number of threads. We can conduct many more experiments like this, and what we come to realize is that the overhead of synchronization has two components to it. The first one is, how long does it take you to find out if you have access to shared data? And what do I mean by having access? It depends on the synchronization schema, but every synchronization protocol ends up with either giving you access to modify the shared data or telling you that you can't. In case of a lock, if you got the lock, you can modify shared data. If you didn't get the lock, you can't. In case of lock-free, if you pass the compare and swap check, you get to commit your results. Otherwise, you go for another iteration of the loop. Either way, how long does it take you before you get the answer to, can I access shared data? That's one component. You always have to do that. But unless you have entirely zero contention, there will be cases when you denied access. And that's the second component of the overhead. If you don't get access, what happens then? And how long does it keep happening? You have to typically wait or compute something else or try to compute the same thing again. So how much time do you lose if you don't get access before you get to try again? So these two components can be different in different synchronization protocols, and it's the total, the sum of them, that matters ultimately for the performance of your program. Usually, it is simpler and faster to determine if you were granted access in a log-based program. You typically have only one shared variable for a good log. That's the flag, which tells you if the lock is locked or not. And you do one read modify write operation like atomic exchange to determine if you got the lock or not. Doesn't get much simpler than that. Log-based programs with a good lock, a more heavyweight lock has more state, more shared variables for you to access. A lock will have only one shared variable, so that's as quick as you can get for the first half of the cost of the overhead, determining whether you were granted access to shared data or not. Now, if you do not get access, that's where there is a large variety of what could happen. In log-based programs, you typically wait. In log-free, you lose some computation. In the case of the queue, if you just put a lock on the outside of the STD queue, you will end up with a longer critical section because the entire push or the entire pop will be under lock, and push has several things. It reserves the slot in the queue, it copies the data into this slot, and of course copying the data takes longer when the data element is larger, so you end up with a larger critical section. In log-free, you naturally write very small critical sections simply because it's actually hard to write a lot of computation and maintain this log-free synchronization protocol, so you're forced to make very small critical sections. In lock-free, they're not really critical sections in the sense that nothing is locked, but it's the part of the code that gets repeated over and over until you get to commit your results. Very often, you can get better performance from both log-based and log-free programs if you can compute something else useful while you were denied access. And we have seen examples of that with various high-performing queues. Remember that concurrency overhead is not a simple thing. It combines several different mechanisms, and when you evaluate different synchronization schemas for data sharing, you have to be aware that you may be trading simplicity of one for the cost of the other, and of course it's the overall cost of synchronization that matters to you. Let's pause to digest this very important insight into the nature of the concurrency overhead. And when you come back, we'll switch gears and look at other practically important, not always obvious aspects of performance. Welcome back. We continue with our analysis of performance in real programs. Moving on to other practical considerations that severely affect performance but are not readily visible in your algorithms and aren't that easily visible even in your code are factors that determine efficiency of memory access. On modern hardware, efficient use of memory boils down to efficient use of caches for the most part. So in single-threaded context, you have only one concern, minimizing cache misses, which usually means minimizing indirections and minimizing random access to data. But in a multi-threaded context, you have a second concern, which is, of course, you want to minimize data sharing, but some amount of data sharing is just inevitable part of your concurrent algorithm, but also minimize what's called false sharing. So false sharing is when two pieces of data that are different are accessed by different threads, but they are occupying the same cache line. And how bad is false sharing? Well, let me show you how bad. This is, again, the increment, but now I'm going to compare data sharing with no data sharing. So look at the bottom line, the one that says no sharing. Each thread is incrementing its own not shared integer. Now look at this line, that's sharing. They're all incrementing the same integer. This is just atomic increment. We have seen that there is some overhead. Now, dashed line, you can barely see it. This is ideal scaling. We start from this time divided by 2 divided by 4. Our no sharing increment is very, very close. But that's only true if each thread increments its own integer that also lives on its own cache line. This line here is each thread increments its own integer, but they are adjacent to each other. So they occupy the same cache line. And you can see that we start off exactly like sharing. So there is no difference between true sharing and false sharing as long as two threads hit the same cache line. So it's not the fact that you're hitting the same integer for increment that matters, but the fact that you're hitting the same cache line. You can see the drop here after 8 threads, and that's because after 8 threads, you have more than 64 bytes worth of integers, so not all integers are now on the same cache line. Starting from this point on, from 8 threads, going from 8 to 16, you basically have 2 groups of 8 threads fighting for the same cache line, but between these 2 groups, there is now perfect sharing. So the total time to do the increments dropped almost by half when you went from 8 threads to 2 groups of 8 threads that are almost entirely independent from each other. I would like to point out that in order to get a good efficiency of caches, you have to break one of the most commonly mentioned and most widely observed rules of software development. And that is the rule, do not optimize prematurely. If you don't optimize for efficient use of memory, it's very hard to change this after the fact. You may try to relay your data structures, but it's harder than optimizing some slow fragment of code. But more importantly, it's actually hard to notice. What you end up with is the performance penalties smeared all over your entire program. So you don't have a single piece of code that stands out. You have this penalty on memory accesses, and it's going to be everywhere in every part of code that accesses this data structure. And if it's some important data structure for you, it could be most of your program. It's actually very hard to find out that you're paying price for false sharing or extra cache misses. There are profilers that will help you with that somewhat, but even the profilers that measure cache misses do not aggregate it by data structure. They aggregate it by lines of source code. So you will see that you have a lot of cache misses, and pretty much every part of your program contributes. You would have to notice that it's every part of your program as long as they're accessing this particular data structure. In the case of memory layout of your data, do optimize prematurely. Think of memory indirections and efficient use of caches and avoiding false sharing before you even know that this is a performance critical part of your code and it deserves extra optimization, because it will be very hard for you to do anything about it after. Another case of very practical impact on performance happens in memory-bound programs. For many years, memory bandwidths have been lagging behind CPU power, which basically translates into memory cannot supply all CPU cores with data at the speed at which the CPUs can process the data. In fact, it only takes between 2 and 4 CPU cores to fully saturate memory bus if they're reading or writing at maximum speed. This is where you get into weird things, like your normal algorithmic complexity suddenly stops applying to you. So if you ever run a sort and see that it's linear in the number of components, it's not because something is wrong with the theory. It's not because you invented a new sort that is faster than n log n. It's simply because your sort, its performance is limited not by actual sorting, but by accessing the memory, reading it and writing it back. And that cost of writing the sorted data back or reading the original data in is so large that for the practical values of n that you're dealing with, it overwhelms the logarithmic terms. Basically, the runtime of the sort is essentially the runtime of copying the data in and out of memory. Of course, sort isn't unique, and this is just the simplest algorithm that can easily get memory bound. In general, remember that the interactions between CPUs and memory are something that critically determines the practical performance of your programs. It's something that may require you to think about it at the early stage of design of your program when you're designing the data structures. And you probably have to optimize prematurely in order to avoid getting into performance traps that are very hard to get out of. With all these pitfalls in mind, what can you do to get a high performing program? Remember that performance begins at the design stage. That's where you lay out efficient data structures. That's where you think about how much data fits in cache and how can you process more of data which is in cache before you flush it back to main memory. How can you minimize indirect memory accesses? And also, this is where you evaluate your synchronization protocols for accessing shared data. You should evaluate them early. You should build prototypes, as we have seen in other parts of the class, where before everything is polished, before the code is finished, before you know all the details, you can benchmark different ways to synchronize access to the shared data and see which ones are faster. As I said, all of this breaks the rule, do not optimize prematurely. Although if you confront some people who advocate this rule on that, they'll point out that what you're really doing is you do not pessimize prematurely. By selecting a good data structure with efficient memory layout and minimal number of indirections, you're simply avoiding problems that you have to fix later. Well, that's a semantic difference. You can look at it any way you want. The bottom line is you have to look at performance at the early stage of the design of the program before you know what will be critical for performance. Otherwise, you may find yourself in a situation where your profiler tells you that everything is critical for your performance and you have no low-hanging fruit to optimize. And of course, we mentioned the profiler many, many times in this class. Your performance-related work always has to be data-driven. Never make any guesses about what's faster. It's very non-intuitive. You will be wrong more often than you're right, even if you have good experience. Subtle things change, new hardware, slight details in the algorithms or data structures make results very different from what you expect based on your experience. Always measure everything performance related. Even if you don't have perfect performance measurement tools, use what you have. Even incomplete information leads you in the right direction, gives you that critical insight that lets you understand the nature of your problems, the source of poor performance. Don't underestimate the value of high-level timers for large blocks of your program. You can leave them in, even running in production, put them in some sort of transcript or log, and it cuts down the time you need to zoom in to find the problem area later, because you know roughly the section of the code that you have to deal with. On the other hand, some of the profiling tools you have probably can do more than you realize. They all measure how long which code takes, they measure CPU time, but some of them can measure the causes of why it takes so long, such as cache misses, instruction pipeline stalls, so on. Finally, remember that if your profiler does not find anything outstanding, if there is no low-hanging fruit, it may be because your problem is not code-centric, but data-centric. It's not that you have a piece of code that is slow everywhere, but you have a piece of data that taints the performance of every code that touches it. There are no good tools for doing it, so you have to do a lot of manual work and use a lot of intuition for that. But try to figure out if your code that is slower than you would like is accessing certain piece of data over and over. This is all I wanted to tell you about guidelines for practical applications of this class for performance of real-world programs before sending you out into the scary real world on your own. If you want to try the scary real world in small doses, consider this exercise. Try to write a program where you know what the algorithmic complexity should be, such as sort should be n log n, if it's a good sort, in the size of the data set. But when you measure it, that program does not show the expected algorithmic complexity, it shows something else. Remember that algorithmic complexity always reasserts itself in what's called asymptotic case. So for example, any sort that uses n log n algorithm will be n log n for large enough n. If it's linear, it's simply because there is a linear component that has a very large constant in front of it, and your n isn't large enough. But again, remember, we're trying to be practical here, that n may be way too large for what you're trying to do. So for you, for the problem you're trying to solve, you may observe the case where the complexity of an implementation differs from complexity of the algorithm as the theory says. Think of how you could achieve such a difference and then try to build such program. If you succeed, it will help you detect these situations in your actual code. They do happen from time to time. It would be good for you to be able to recognize this, because obviously if it happens, what it means is you can't fix the problem by improving the algorithm. It's not a simple task, but it's doable. With what you've learned in this class, you should be able to come up with some examples. Go and have fun with it. We just went over several hand-waving examples where in a concurrent program, I was trying to show you how sometimes you can't really tell whether your queue works as a queue or not. This is all very loose talk, and there are several levels of ordering guarantees that you can talk about more formally. For example, there is sequential consistency, which is a very useful feature in understanding programs. And what it boils down to is, again, there is a more formal definition, but your mental model should be kind of like a zipper. Every instruction is executed one at a time. You have two multiple streams of instruction if you have two threads, but in each of these streams, at any time you pick one instruction from one of the streams and execute it. Then you pick the next instruction, could be from the same stream, could be from another stream, and you execute that. So in case of a well-functioning zipper, you would alternate, but imagine a broken zipper where several teeth go in all at once. That could happen with sequentially consistent programs. So you have this flow of instructions, but you can always imagine a specific order. that order still varies. It only has to be like in order that it's written, but you can have one instruction from the first stream, two instructions from the second stream, then three instructions from the first stream, or 1, 1, 1, 1. Different times you run it, you'll get different orders. So you don't get reproducible results. But there are certain guarantees. Some kinds of results, because of this ordering guarantee, you just cannot get at all. Another way to think of it, if you need a mental model, is imagine multiple threads executing on a single CPU system. Well, that CPU can only run one instruction at a time. Again, forget about hyperthreading. One CPU, one hardware thread. So that CPU can only do one instruction at a time. Two threads are arranged somehow by the operating system to run, but the CPU can only do one instruction at a time. What you would get is some number of instructions from the first thread, one or more, then some number of instructions from the second thread, and so on. One of the side effects, for example, we have spent a lot of time talking about memory barriers. Well, you don't have that problem here. If a value is written into memory, it becomes visible to all threads because instruction with all of its side effects is completed before the next instruction starts. That's part of the ordering guarantee. On a single core system, you just get that. There's nothing else. On multi-core systems, you could get that, but it may come at a significant cost. That synchronization between cores is expensive. If you were willing to give up that sequential consistency, you could reap significant performance gains at the cost of some torn hair. Debugging gets a lot harder, and actually even understanding your data structures gets a lot harder. Your concurrent data structures may not necessarily have a mental model that you can use that assumes a particular order of operations. In fact, the higher performing ones often don't. Let's see an example of how you would sacrifice profitably sequential consistency. Here is a queue. We have actually seen it before. I'll show it to you again. We'll explore it here briefly. It's an array of atomic pointers, each pointing to a single threaded queue. Here is how I'm going to use it. So I have two threads that are trying to operate this queue. The first thread does an atomic exchange of the pointer with null and keeps the return value. So now that thread basically took the ownership of the single threaded queue. It replaced the shared atomic pointer with null, so nobody else can get to that queue, and that thread keeps the only pointer to this queue in existence as its private local variable. The thread then proceeds to work on the queue, doing enqueuing or dequeuing, whatever. Second thread comes in and wants to operate on our queue. It begins from the beginning of this array, but the first element is null, which means you can't get to that queue. So it rolls forward along the array. The second element is not null, and oops, now it is. Because the second thread just exchanged it with null, again atomically, and took ownership of the second single-threaded queue. When the first thread is done, it will release its ownership of the queue by restoring the atomic pointer, and so on. This queue is not sequentially consistent. It's only a queue in a statistical sense. Elements mostly come out in the right order. A lot of things are happening at once here. Even trying to kind of understand how it works and what guarantees it actually gives you, it has very few, is hard. But it's actually pretty fast if you can live with it. It's a lot faster than a spin-locked queue. It's even faster than a reasonably good implementation of the log-free queue. Now, you could come up with a better implementation of the log-free queue, but the one I benchmarked here isn't so bad. This trilog queue is really fast. If you thought that things couldn't get any stranger, they can. Let's look, for example, at the list. So here is a list. I'm going to start scanning the list. So I have a pointer that scans from the head. So from the head, the first element is 1. And while I'm doing that, I'm going to start modifying the list on another thread. So this other thread is preparing to insert a new element. If you remember how the list works, you first prepare the new element kind of off on the side. You link its next pointer. You don't yet link it into the list. In the meantime, the scanning thread continues along the list. Now it sees 2. While that's happening, I finally got to where I'm doing an atomic change of the head from the old value to the new value. I did that. Now 4 is linked into the list. Now I have inserted an element after 2. I have inserted element 3 after 2. I can do that on another thread. My scanning thread is still dealing with 2. Maybe it's printing them. Then I have yet another thread that deletes element 2. but I have a well-written list, so I don't have any dangling pointers, and the fact that my scanning thread points to element 2 holds that memory alive, prevents it from being deleted. It's just not in the list anymore, but it hasn't been deleted yet, so everything here is working fine. I don't have any crashes, I don't have any pointers pointing to deleted memory. My scanning thread finally advances to 3, and that lets me delete the list element 2, and I finished scanning the list. Now ignore the scanning thread for a moment. Forget about it and look at the state of the list. I had 1, 2. I inserted 4, so I had 4, 1, 2. I added 3, so I have 4, 1, 2, 3. And I deleted 2, so now I have 4, 1, 3. If I could observe the list under a debugger, I would see that the list was in one of these 4 states. It changed through this sequence of states. If I looked at what my scanning thread had printed, it printed 1, 2, 3. The list was actually never in that state. There wasn't any moment of time when the list contained elements 1, 2, 3 and nothing else. I have a correct program. It doesn't point to any corrupted memory, it doesn't point to any deleted memory. It's correct in every way. It doesn't have any race conditions, but when it scanned the list, it showed me a state that was never there. That's actually how it should be. That's how a concurrent list works. You can't have it any other way. That's what it means to have a thread-safe list. So this particular list actually has sequential consistency, and it still does it. So you just have to get used to this. So in general, concurrent data structures are weird. The state that you observe by scanning them isn't necessarily the state they have ever been in. You kind of have to get into that mental state to understand it. You have to wrap your mind around it. Once you do, you can also start thinking about it from a different point of view, from the opposite point of view. Since I don't actually have the guarantees I'm used to from these concurrent data structures, and I often can't get these guarantees, or at least if I have those guarantees, I can't actually observe from the program that I have them, what could I get away with and optimize my performance? The example of that was the trilog queue. I noticed that in many programs, I actually can't detect that the queue returns its elements in a strict queue order. I figured I can get away with some slight statistical deviations from that order and get much better performance. In some programs, I can't get away with it. There are programs which would detect this. So you have to think carefully what you can and cannot get away with. But it's a useful exercise. It will probably take you a while to wrap your mind around these weirdnesses of concurrent data structures. But for now, all I can offer you is a short break before the next section, and then we get to learn about more data structures. So we had pursued this line of thought about how concurrent data structures are observed in these strange ways, how they change while you're looking at them. Now I want to strike out in a different direction. I have only shown you in details few data structures, and I really can't teach you everything about every data structure there is. I have to at some point give you general pointers and set you on your own path. In general, the data structures that have 1 or 2 fixed entry points like stacks and queues, they're fairly easy. You can easily lock them, and if you want to try for slightly higher performance, sometimes you can get it by a simple lock-free synchronization protocol if you take advantage of particular limitations of your problem. And there aren't that many different types anyway. There is a wide variety of data structures that allow access to a lot of different parts of its state: lists, arrays, trees, hash tables. You can read basically any part of it, and you can modify any part of it. One thing about these objects is they're also very hard to do with locks in any efficient manner, because you really want to permit concurrent unrelated accesses to totally different parts of your data structure. For example, if you have a list and the list is very long, there is absolutely no reason why insertions or deletions of elements that are many elements apart should block each other. Similarly, if you have an array and you're updating one element while reading another, and they are not the same element or not adjacent elements, again, there is absolutely no reason why you should block one of these accesses for the other to proceed. You want them to be completely concurrent, and at the same time, if you happen to hit the same element from two different threads, you want to avoid a data race. You can't have a single lock on the entire data structure, because that would lock unrelated accesses. You could try to have a lock on every element or a lock on a group of elements. The main danger here is actually not performance. The main danger is that you will deadlock. So you have two locks, lock 1 and lock 2. One thread gets lock 1 and tries to get lock 2. The other thread gets the same two locks in opposite order. You get lock 2, then you try to get lock 1. That's a deadlock. The common way of preventing that is try to acquire locks in opposite order. With these data structures, you don't always have that luxury. You may have to acquire these locks, for example, in the order in which you're scanning the data structure. If one scan is forward, the other scan is backward, you may not even know that you're going to need the second lock until you got the first one. So this is where lock-free schemas really become very important, and I have shown you one for the list, and there are a lot of them. So for the single linked list, we have seen just compare and swap. If you have a doubly linked list, slightly more complex data structure, the simplest thing you can do is have two compare and swaps completely independently for the forward and backward linkage, and you will have an interesting side effect that your forward and backward lists aren't updated at the same time. So if you run a forward and backward scan, you can get different lists from forward and backward scan, which is kind of weird, but again, in this concurrent world, it happens all the time. If you do something like a tree, you often need to atomically swap two pointers. If you start pursuing it in the same way as what you did for the list, you run into a dead end. Why? Well, you have two atomic pointers. You can perform an atomic operation, so you can replace one of them, then the other one. But while you're doing the first one, another thread can read it, and then it can also read the second one. So this total transaction, replacing two pointers, is not atomic. Here is how you atomically swap two pointers. You have an array of pointers, and the pointers are not atomic. What is atomic is you have this integer which can be 0 or 1. The way you read the pointers is you don't actually read two pointers directly. First, you atomically read the index once. And after that, with that index, you access both pointers. And let's say the index points to the left and the other pointer is the right. So now, if you atomically change I from 0 to 1, you will do effectively an atomic swap of two pointers. Tricks like this is what lets you form more and more complex lock-free synchronization schemas. I can't possibly teach all of them to you. Hopefully, I have given you some ideas, some lines along which you can think when you build your own data structures. There are a lot of special cases in which lock-free data structures are particularly effective. Very common cases, you have a large set of data, you have a relatively infrequent stream of updates, but you have constant read accesses like searches or just scans. Basically, you're reading it all the time. Well, if that's the case, you want your writes, updates, to receive priority, because if the writer will wait for the readers, there are so many readers, the writer will probably never get its turn. On the other hand, if the readers always have to wait for the writer, that's no big deal because writes just don't happen that often. Again, this is a particular application. It happens to be a very common one. So for this kind of application, there is an interesting synchronization protocol that is called sequential lock. Here is how it works. The entire atomic shared part of it is this atomic version number. So the writer does a very simple thing. It increments the version number, does the update, increments it again. Version numbers start from 0. Version number even means that writer isn't currently updating. Version number odd means you're in the middle of the update. Now, this does not synchronize multiple writers between themselves. Often, if you have infrequent updates, you actually don't need the bandwidth of multiple writers. You can do one writer thread. If you have multiple writer threads, you just queue it all into one thread and have one thread actually do the updates. If you need to synchronize multiple writers, you have to do something else to basically establish which writer gets to go at any time. But the writer that actually has a go to update your data structure always does this. Now, you can see that the writer doesn't get blocked by anybody. When the writer wants to do an update, it just goes and does it. The reader is the one that gets to wait. So first of all, the reader has to wait if the version is currently odd. It means update is in progress. You can't really do anything while an update is in progress. If the version number is even, you can read the data as much as you need, but what you have to do is you have to make sure that the version number at the beginning when you started the read and at the end when you finished the read is still the same, which means the update hasn't happened while you were reading. And if the update has happened, you have to start again. Now, this is not lock-free. And why is it not lock-free? Remember, lock-free guarantees that at least one thread makes progress at any time. Here, if the writer stops in the middle of update and doesn't do anything, the readers also can't do anything. The readers will just spin on that loop for update and progress. So this is not lock-free, but it does have that advantage that multiple readers totally ignore each other. They don't block each other at all. And basically nothing interesting happens as long as there is no writer, but the writer immediately gets priority. The readers cannot block the writer. This is just, again, an example of a more complex synchronization schema. It's something to show you how you can generalize these simple building blocks that I have given you, because I can't teach you all of the possible synchronization schemas and protocols for what you might need to do. I can hopefully show you how to think about these problems. And that's what I'm trying to do by giving you examples of how you generalize. There are lots and lots of synchronization schemas. I have shown you some. They all have different trade-offs. In this case, the writer basically halts all the readers instantly. That's a trade-off that we wanted to make, but it's a trade-off. For some other case, it may be a significant disadvantage, then this lock is not for you. You analyze your trade-offs, you decide what's more important to you, and then you come up with synchronization protocol for concurrency that has the right trade-offs. I wish I could keep teaching you more and more, but our time is not infinite. It is, however, time for you to strike out on your own. We have talked a lot about how you can have a data structure's performance impacted by non-algorithmic things, such as cache coherence, accessing memory efficiently or inefficiently, amount of data sharing. Try to create a program that uses some data structure in a way where the runtime does not match the algorithmic complexity that you learned in school. Here is a simple example. Linear search. What you have learned in school is it has the complexity of order n. If you try a linear search on a vector and a linear search on a list, assuming list has somewhat random memory allocation, you will have very different results as you vary n, the size of vector and list, because they have very different cache behavior. Try to catch this sort of real-world difference between what theoretically should be the same thing. It will teach you what to pay attention to when you run into the bad side of this phenomenon in your own program. Have fun with it. Welcome back to the class on high-performance computing in C++. In this chapter, we're going to take a more general look on data structures for concurrency. In earlier chapters, we have examined and taken apart and studied in great detail several specific data structures. We picked the simpler ones so we can actually explore them in a reasonable time, and I have shown you a lot of technical details. So now I want to give you some more general ideas about how to approach the design of data structures for concurrency in general. How you take the things you have learned on some specific simple data structures and apply them to the things you need, because you probably don't just write lists and queues, you have other things you need to do. So how do you make what you have learned useful and applicable? Well, the concurrent data structures, they're just weird in several ways. You have to deal with the fact that they can be updated by one or more threads. One makes it a lot easier, while at the same time they are observed by one or more other threads. Well, that's what makes them concurrent. Now, if you have multiple threads, they're all observing or modifying the data structures in time, and you have multiple events happening in time, and you want to talk about them as these two events happen at the same time, and this happens before that, and so on. But in order for you to actually even describe it using this language, you have to establish what's called happens before or happens after relationship. If you can't, then you can't really say about some events how they happen. As far as you're concerned, they're all happening at the same time, even if they may be happening minutes apart or hours apart. But if you haven't established this happens before relationship, you can't know. So an example to make it less abstract. If you have one thread that successfully acquired a lock, that thread will proceed through the critical section, and it will finish the critical section before another thread can acquire the same lock. That much is guaranteed. But if you didn't have an event like this, like acquiring a lock or issuing a memory barrier, you can't really say what happened before and what happened after. And that takes some getting used to. Let's go back to the example of the queue, well, because we studied it and because it's kind of easy to understand, to see how this loosely defined order manifests itself. So I have a queue, and if I could halt it under debugger, pause the entire program, I would see that my sequence that is the underlying implementation of the queue has these, let's say, queue of integers. So it has 1, 2, 3, 4, and so on. Now I resume my program, I let it run again, and I have two threads that are reading from the queue. I have already seen in my debugger that 1 is in the sequence before 2, so I would expect 1 to come out from the pop operation first. Similarly, I have two threads waiting to push data into the queue, and if I watched in the debugger how they do it, I would see that 13 went into the queue first. 13 went into the sequence, then 14. After the push finished, I stopped the program under debugger, and I watched, and I made sure that, yep, 13 is before 14. I let the program run for a while until 13 and 14 make it to the head of the queue. Would 13 come out first or not? It depends a lot on the queue implementation, but let's think about it just purely from my program point of view. How would I actually observe it? I would call pop front, which on the queue, this std queue is just pop, it calls pop front on the underlying container, and I would call it twice, and I would just, let's say, print what came first and what came second. I can do that. Let's say I'm doing this on two threads, and I know that 1 is in the sequence first. Just before I called pop front for the first time, I halted the program on the debugger, I examined the sequence, and 1 is in the queue first. If 1 is in the queue first, the first pop front to run will pull 1 off the head of the queue, assuming you have a queue that actually works like a queue, it pulls the first number of the head. Let's assume that that's the case. And then the second call to pop front runs on the other thread, and it happens after the first one. And how do I know? Well, I'm watching it under debugger. I didn't actually synchronize the events, but I have this sort of God's eye view of the entire system. And that's actually where the crux of the problem is. It's this God's eye view. It's a bit of a cheating for concurrent programs. You can, of course, observe the program under debugger, but when the program runs by itself, you don't have that view. You only see what you can observe from the outputs. In this case, whatever these functions return. The first pop front got 1, the second pop front got 2, but they got it, they just read it from the underlying array. Now they have to return this value to the caller. They have to store it into the caller's memory, and they have to return from the function before you can print anything on either thread. And let's say that the thread that pulled 1 off of the queue is preempted, and the thread that pulls 2 off of the queue gets to complete its function call first. Every instruction is separate in the sense you can have a thread preempted at any time, so you can pop the first element within the pop front function, and then the thread takes a pause and another thread gets to compute. Entirely possible. The result is that you will print 2 before 1, even though if you actually watched instruction by instruction under debugger, you would see that 1 came off first. Now you're not running your program in real life under debugger all the time, so forget the debugger. You're running it now just watching the outputs, and you printed 2 first. As far as you know, 2 might have been popped first, so you don't actually know that the order of the elements coming out of the queue was 1, 2. It might have been 2, 1. That's what it appears to you that it was 2, 1. So this queue, even though it actually, in some sense, maintained the order, the sequence was never violated. 1 was always sequenced before 2 in the queue. But because you didn't have the synchronization on returning the control to the caller, it didn't ultimately matter. Well, similarly, on the other end of the queue, I'm running it under debugger again, and I make sure that push of 13 started running before push of 14. I could, for example, print when push is about to run, and let's say push of 13 again prints its thing first. I'm about to push 13, and then it prints I'm about to push 14. That's fine. Push is just a forward to push back on the container, so you invoke pushback of 13 first, but once you are inside the function, all bets are off. There is no synchronization in there. Both of them have to get a slot from the tail of the queue. The function that was called first could manage to take the slot later. 2 threads running on 2 CPUs depends on how the operating system schedules them, how fast the CPUs access memory. You have a cache miss, one of them ends up running a lot slower than the other, thousands of reasons why it could happen. Even though you called push 13 before pushing 14, 13 could end up stored into the queue later. Again, without this debugger, you can't actually know this. So all you will eventually see is that you called push 13 first, and then 14 came off the queue before 13. So again, as far as you're concerned, this concurrent queue isn't really a perfect queue. It violates the order. Take a moment to think about all of this. When you come back, I'll try to put some system on this that will maybe help you to understand it better. Welcome to the final chapter of our class on high-performance computing in C++. If you're here, you have shown dedication and perseverance to hang on to it throughout this entire class, and I want to thank you for that. And before I let you go, let's review what we have learned and see where you go from here to continue your learning. We spent a good half of this class just getting really close and learning all the details about hardware, and we focused on memory system and on the hardware that provides the concurrence capabilities. Looking back on it, why did we do that? Accessing memory incurs huge penalty. It's maybe 100 times slower than, well, not accessing memory. Now, of course, no program can avoid accessing memory entirely, so you can't mine all of that 100x potential speed up, but what it shows is that there are big resources for optimization. If you could reduce or optimize accessing memory, you could get some of that huge penalty removed from your code. We have seen how different data structures, different ways to organize data, different ways to process data in batches of large or small size could change the performance of your program by literally orders of magnitude, from keeping your data mostly in closed caches to accessing main memory every time. We have also spent a lot of time on concurrency, and that is because while the individual CPUs themselves are getting somewhat faster and there is something to be made from that improvement, for the most part, the entire progress of CPU development in the last years have been in multi-core systems. So depending on how many cores you have access to, you could be looking at speeding up your program 4 times, maybe 50, 80, 100 times, depending on how many cores you have. And there is a big difference between doing it poorly or doing it right. As we have seen, some of our well-scaling programs have shown close to ideal scaling for a small number of threads. We explored the problems you run into for a large number of threads, and some other ways of writing programs we have seen don't scale at all. So again, there is a large potential for optimization here. At the same time, just because we only have so many hours in the class, we have not at all covered other available sources of performance, such as optimizing for the best CPU utilization on a single core or vector and other advanced instructions. That's something for you to learn from another class or on your own. After we were mostly done with hardware, we reviewed different ways to synchronize concurrent programs in multi-core systems. So these are things like locks, spin locks, atomic operations, lock-free programs. And again, why did we spend so much time on that? Because we have seen how much impact it can have on performance. Choosing the best synchronization options compared to just picking what's easily available can give you, in some cases, maybe 10x or more of speed up. Memory model was the focus of our attention for a while. And that was because data exchange through memory is really at the heart of concurrent programming, and it has to be done both correctly and efficiently. So we have seen the memory model in all of its details. Now you should have good understanding of what the critical section is and how it is arranged, and what the different memory barriers are, and what of that is required for your program to be correct, and how much these features cost performance-wise, so what should be avoided if you don't need it for correctness. We also considered how to use the memory efficiently in concurrent programs. If in single-threaded programs, the memory is very important because of how expensive it is to operate on it, it becomes even more important in concurrent programs where you actually don't have enough bandwidth to satisfy memory requests from more than 2 or 3 threads at the same time, unless you're using caches efficiently. So even larger potential for optimization gains, or if you look at it the other way, potential for huge slowdown if you don't use it the optimal way, exists when it comes to accessing memory in multi-threaded programs. Again, there are areas we have not had time to cover. While we had a pretty comprehensive review of synchronization, there are even more hardware features that can be used to avoid data races and synchronize data sharing in your program, such as transactional memory, low collision. These are new features just coming out. We didn't spend time on them, but as such new things are invented and made available, you need to keep your learning current and be aware of them. We completely passed on distributed computing. All of our concurrency was shared memory. There is another huge area of distributed computing that we haven't touched at all. That's something, again, you can learn on your own. And we didn't talk about heterogeneous systems such that CPUs with GPUs, other accelerators. Again, there is only so much time we have to cover all of this. These are all the areas that you could study and practice if you wanted to continue learning about high-performance computing. We moved then from nuts and bolts of concurrency and efficiency to a higher level of data structures specifically designed for concurrency. And we talked about how they should be designed, how they should be implemented, what are the thread safety guarantees, and how they should be built into the design of your data structures, because they're really part of the interface, only less visible, which makes them all the more important. We reviewed quite a few different data structures, but they were all examples of what you could do. The techniques you should learn to build your own data structure, some of these you could use as is, but for the most part, the value is in teaching you how concurrent data structures should be built. We also reviewed trade-offs inherent in designing such data structures, and that's true whether you choose to build lock-free data structures or not. You trade complexity for performance, you trade some of the functionality for performance gains, and so on. And we have seen a lot of these trade-offs, how they work, and how you could decide on what to give up in exchange for what to gain. I have shown you how to measure performance of different synchronization schemas for concurrent data structures. The same logical data structure can be designed in many different ways, and they'll have different single-threaded performance, but also totally different scaling, and we have seen that, and I have given you some tools to estimate which of the approaches to concurrency, to concurrent synchronization, will give you the better result for your specific needs, and how to measure it early, and how to estimate it early, how to build the required performance potential into your design, and then verify by measurements that your design can meet the required performance goals. At the same time, of course, there are plenty more data structures we haven't had time to cover, and there are many lock-free synchronization protocols, many more than we covered. Hopefully what I have taught you will let you understand them as you encounter them in literature and invent your own as your needs drive you. Very importantly, we have learned how to measure performance. Actually, I take that back. First of all, we learned that it's very important to measure performance, and only then how to measure performance. To that end, we have learned about writing benchmarks, using profiler tools, using timers to measure performance in your own programs. I tried to show you how to collect the performance measurements that are actually relevant for your applications, that it would guide you toward writing actually faster, more efficient programs. There are many more performance measurements tools out there. You may have access to some of the ones that I did not show you, but hopefully with the information I have given you and the exercises I made you go through, you will be able to quickly pick up on how to use any of those tools or how to find tools that maybe fit better your specific needs. So overall, what have we learned? You have gained much better understanding of the hardware and its effects on performance. Specifically, we covered multi-core systems and memory systems and the combination of the two. We researched and reviewed and had examples of low overhead synchronization. We studied thread-safe, scalable, high-performance data structures for concurrent application, both log-free and not log-free. And we have learned throughout the entire class how to measure performance. But this is all current knowledge, this is all good, but perhaps the most important lesson that I wanted to teach you is the understanding of how these hardware systems work, how the concurrency works, how the data structures do their magic, and how can you, on your own, when you encounter a different hardware system or a different data structure, understand the same level of details about it. How can you keep learning about things that I don't know about, that may not exist yet, but you will encounter in the future? And this learning how to learn is the most important skill that I can teach you. Throughout this class, I have given you, at the end of every chapter, some bit of independent study, homework if you're still fresh out of college. For this chapter, it's different. You're done. You graduated from this class. Your homework now is your work. Apply the knowledge you have gained, keep expanding your knowledge, use this knowledge, use this learning to write some good, efficient code, and try to enjoy it. It goes better if you like what you're doing. It would be unfair for me to send you out to do that last unlimited homework assignment without at least pointing you to some of the more tools that you could use on this way. Now, the challenge I'm facing is that there is a good chance that any specific tool I point you to will be obsolete, or at least the web page will be at a different location by the time you get to this class. So I'll try to give you something more general. We'll start with the tools for performance measurements. Those are, I feel, more comfortable giving you the specific tools. Even if these particular tools will be replaced by other tools, fundamentally, they're kind of all similar to each other. There is progress, there are improvements, but if you learn to use one, you can learn to use another one. So we have used Google Benchmark. There is a very similar benchmarking library called Nonius. In addition to hardware timers that I have shown you in the class, probably the best source of timing in your program is now the C++ Chrono header, now that it's in the standard. And I recommend Howard Hinnan's blog on this. He has links to his CPPCon lectures where he explains how to use this header. He has some other information on it. We have used Perf. It's a decent profiler. Liquid has some other features that you may find useful. There are several commercial tools. VTune is probably the most well-known and the most full-featured of the ones I know. Again, there are other tools that are similar in capabilities and functionality to these. There is no wrong way here. As long as the tool gives you what you need, it's the right tool for you. As far as what can you read to learn more, I do recommend the book by Anthony Williams, C++ Concurrency in Action, and for more current information, his blog. A lot of talks on high-performance computing, log-free programming in C++ can be found at CPPCon and CPPNow archives. They're all on YouTube. Jeff Preshing's blog at this URL that I have on the slide is a good source of information. There are some interesting articles. Perhaps even more importantly, there is bibliography. There are references to other news sources as they come up, and therefore I can't give them to you yet because I don't know them yet. They haven't appeared yet, but as you read the bibliography on Jeff's blog, you will find references to them. Some of the older information, but still very useful, Hans Bohm's page explains a lot about C++ memory model and why it is the way it is and how did we get to the decisions that were built into the language standard. And Herb Sutter's concurrency blog is getting a little old by now, but still has a lot of interesting things on it. I recommend reading it as a general background education on concurrency. I want to thank you for spending your time taking this class, and I hope I'll see your code someday as an example of great efficient programming.